Krásné dobré ráno, dámy a pánové.
Good morning, ladies and gentlemen. I would like to invite you to your tables, our conference tables. We will start in 2 or 3 minutes.
We are going to start in about, let's say, 3 minutes. Krásné dobré ráno.
Good morning, ladies and gentlemen. Welcome on this sunny Wednesday, the 5th of June to 2024. My name is Justin. It will be my pleasure to accompany you today.
So get your translation devices if you didn't get some yet. To znamená, že pokud nerozumíte náhodou někteří z vás ostatním jazykům, tak vám hned teď v úvodu vám nabízím, abyste si vzali překladatelské staničky, které
So please take the headsets if you don't understand any language. Today is the second day of innovations in the protection of the environment. We are glad that you came today. We would like to welcome all of you here and online. You can switch between Czech and English channels. Our today's conference is organized as part of Ecosystem and Change of Climate program. It is funded by Norway Grants until from 2014 to 2021, and the Czech partner of the program is the Ministry of the Environment of the Czech Republic. Last year, 165 projects were supported, and they focus on the changes in climate in municipalities and regions. We probably heard this information already yesterday, but for all of you who are here today, it is new. But for those who were here yesterday, you hear it for the second time. We would like to introduce to you projects focusing on innovation of and protection of the environment. Today's program focuses on a very narrow issue, micropollutants in surface waters, focusing on residues of drugs in waters. We are convinced that this topic is very important, and that's why we are glad that today, on the International Day of the Environment, which is actually today, today is also the day of vegan burger. That's just a coincidence, too. And we are glad you will spend today with us here today. At the beginning of the second day of the conference, I would like to welcome the director, Mr. Marcin, from the State Environmental Institute. Good morning to everyone. I would like to welcome all of you here, dear guests, also in the online environment. I would like to welcome you here in a beautiful environment of Spojka. And I would like to start the second day of the conference. I see there's about half of new faces here. So at the beginning of the conference, I would like to guide you through some dates that have already been mentioned by the host. This is a program, the environment financed by Norway Grants, and as I already said yesterday, I would like to emphasize it. The program makes it possible for us to focus on areas that are not funded as a standard or are not addressed as a standard. That means innovative programs. And this whole conference is about sharing innovative approaches in the environment. Today we will talk about pharmaceuticals, micropollutants. It's a very interesting topic. Until now, we had no possibilities of funding, and there was no essential massive program that would deal with these issues. So we really appreciate that as part of this conference, we can introduce to you these areas, talk about the biggest risks, and say what the next procedure will be. The innovative projects are about looking for solutions, what is at risk, what is happening, and what to do further, how we can deal with the potential risks in terms of technology available, and what kind of financial resources we can use. The Norway Grant program in the area of water protection is one of the 4 areas. Yesterday, we had a possibility to discuss projects concerning ecosystems and protection of biodiversity. Another area is air protection, and also an important topic, change of climate. The water protection was supported as part of 3 calls. I will just remind you that these the calls for acceptance of applications were named after places in Norway. So these calls had names according to towns or locations that have something to do with water or somehow are connected with water. So as part of Norway Grants, we have Olesen, hopefully I'm pronouncing it correctly, Olesen call, which dealt with infrastructure, so that we are even able to capture the area of micropollutants. Another one is called Trondheim, is also connected with waters. It's a beautiful town, and it made it possible for us to verify the technologies as part of research or semi-operations in some cases, often in water treatment facilities at universities and operators in various river basins. Technologies focusing on monitoring and removal of micropollutants. So this call, consisting of 6 projects, should show, and you will have a possibility to discuss some of them here today, should show whether these technologies work or not, and what are other needs, what we are still missing, what needs to be done. And another call named Rheine, it's a beautiful town, made it possible to support projects focusing on awareness on these topics. These are 3 areas that Norway Grants started here in the Czech Republic. They opened these topics in the Czech Republic, and so we are able now to focus on them thanks to these subsidy programs. Of course, the topic is not new. Also, other countries address this topic. In Norway, NHP program, our colleagues in Romania or Poland also deal with this topic. And I think that everyone at the moment knows that this topic is getting more and more to the forefront, because the quality of drinking water, of course, is a burning topic. Now we have floods here or heavy rain, as you know, but our colleagues from Norway mentioned yesterday that they actually suffered from drought on the just the opposite, but quality of drinking water definitely is an important topic. Thank you for your participation, for your attention. Thank you for presenting your presentations today, and I would like to wish you a nice and inspirative conference today. Have a nice day. I would like to thank you for your applause. You know that the whole program is supported by Norway Grants. We would like to welcome the representative of the Norway embassy here in Prague. Good morning.
So, good morning. I welcome everybody here. My name is Helena Kinska. I work on the Embassy of Norway in Prague, and allow me to apologize the absence of Mr. Ambassador. Unfortunately, he is ill, and he is being treated now in Norway, but he greets you all cordially. Anyway, so I was here yesterday, and the conference was very interesting. Those topics were, for me, kind of easy to grapple, the invasive species of animals and species. And the topic we have today is more technical. And I think there would be fewer people coming, but I see now that there's enormous interest, and that there are many experts here on the pollution topic, because this is very highly important topic and will be ever more topic. Interesting. So the conference is part of the environment program, as you have heard, funded by Norway Grants. Nevertheless, the Norway Grants do not actually include only this program, the Czech program. We have 11 programs of various focuses, and I would like to say that this one, environmental and climate topic, is one of the most important, and it's a topic going across the program, so it's reflected also in the other programs, especially in the science and research program. And now a new period of the EEC and Norway is being under discussion, and we know that the chosen topic, transformation, is a key topic, and we will hope that it will be possible to negotiate this as soon as possible, and you will be able to continue your activities. The main objective of the EEC and Norway funds is to decrease the differences in Europe, both social and economic differences or gaps. And the projects supported through these programs do really contribute very much to this by increasing quality of life, but also competitiveness and prosperity of Europe. The second objective is international cooperation, and it's very nice to see here partners from the program of the Norwegian Environmental Agency, and also partners from other countries who actually add the international dimension to the event today. As far as Norway is concerned, innovation, water pollution, these topics are of course very important, and this topic, contamination of surface water, is new, and I believe that the knowledge will be usable also in Norway. We will hear today one more contribution from Norway focused on microplastics in marine waters. Of course, it's a topic we don't have in marine waters, but the microplastics are also an enormous problem here in our domestic waters. So it's yet another important topic of our Czech-Norway cooperation. In conclusion, let me actually show you one video some of you saw yesterday. It is greetings from the ambassador. And the video is introductory video to a documentary series shot by the State Environmental Fund for its project. All these topics are available online, so you can have a look at them. Thank you for your attention, and I wish you to have an inspirational conference.
I think we need during these times, we have so many challenges, also so many common challenges, to join forces. And this is actually what we try to do with the Norway Grants. We try to join forces to focus on important questions that's essential to both our countries. And I certainly hope and I expect that to continue in a way that we grow even closer and are even better prepared for the future.
Norské fondy cíleně zaměřujeme zejména na podporu inovativních řešení, pilotních projektů a hledání dalších cest právě i prostřednictvím té mezinárodní spolupráce. Projekty, které mohou něco ukázat, nějakou cestu si v uvozovkách ověřit a samozřejmě i motivovat jiné dotační programy převzít a pokračovat ve financování některých projektů.
We try to kind of tailor the programs in a way that it's good for the receiving part, but also good for Norway. I mean, we change knowledge, change information, we learn from each other, and that's good for both parts. So they are changing according to what's most needed at any time.
Samozřejmě Norsko má zájem investovat do oblastí, kde má buď možnost něco získat, ale samozřejmě kde může i něco nabídnout. V tomto případě Norsko a životní prostředí mají k sobě samozřejmě velice blízko a není teda překvapením, že oblast životního prostředí v případě České republiky má největší alokaci v případě norských fondů.
Well, the relation between Norway and Czech Republic are generally very good. I mean, in all areas, we are kind of like-minded. This is a programs and projects that's beneficial to all of us, and it actually binds us together and makes us all better prepared for the future.
Děkuji.
Thank you, Mrs. Dańska and the ambassador. In mediation at Chmielnicka said that we don't have much common with the Norwegian marine waters. It's not absolutely true today because you are sitting on chairs produced from plastic materials chosen in the Nordic Norwegian Sea, 100%. So the interconnection in this Polka Hall is here. But before we start the whole conference, ladies and gentlemen, allow me to make a few organizational points. As in every conference, there may be kind of changes during the program today. So the agenda that you have in your tables are very probably correct, but not 100% valid. So it may happen. Not maybe, but definitely during the first presentation, the presenter will have two presentations at once or in one, because the other lady actually apologizes for being ill. So the times that you see on the agenda is just orientation. We may end up and sooner or later. So I would like to ask the speakers for this reason to keep the 20-minute limit for their contributions. You can pick up your interpreting headsets. For today, we have Vendula Maldonado and Bohumilshek as the interpreters for today. Good morning. My name is Houston. And should you have any wishes or desires or complaints during the day, please contact me and I will meet your wish or not meet your wish. Two possibilities. And so we have Aneshka here, photographer, kind photographer. So if you want to get a picture of yourselves and somebody else, please go contact her. Those who have announced you have some food limits that during in the dining corner, there will be some snacks and refreshments. You will have a special table which is directly prepared for you. And we offer to all of you to you make use of the outdoor terrace because of the nice weather today. So during the breaks, if you don't want to eat, if you don't want to go out, you can watch on the screens around us videos concerning these supported projects. I believe that from the organizational point of view, I've told you more than you wanted to hear, and probably you will remember something of what I said. If not, I'm ready here. And with regard to speakers, I will choose this notepad to wave, if they are over the limit. The first speaker I invite to open the conference today, it's the lecture, The Fate and Effects of Micropollutants in Aquatic Environment from the University of South Bohemia. It's Professor Randak from the Faculty of Laboratory Environmental Chemistry and Biochemistry. So thank you. I would like to thank the organizers for inviting me to this event, first of all, and also I would like to apologize. My colleague, Mrs. Fodorova, she can't participate, she can't attend today because she's ill, and I'll try to kind of convey her presentations or lecture to you. It's not quite my oyster, so please be actually tolerant to me. So should you be interested in some topics, we can have a discussion afterwards. So the first lecture is kind of introductory lectures, and it focuses on the incidents and effects of the so-called micropollutants in aquatic environment. The first introduction, I would like to present my department. I'm from the University of South Bohemia, as mentioned before, and the Faculty of Fishery and Water Protection. I work in the Laboratory of Environmental Chemistry and Biochemistry, and it deals with the development of prospect analytical methods which are targeted to detecting various kinds of micropollutants in the components of the environment. And so we are developing methods to detect pharmaceuticals, pesticides, and other pollutants. And at the same time, we try not only to monitor the occurrence of those substances in the environment, but also to find out their effects on organism in laboratory or field conditions. And we also cooperate with various companies dealing with the technologies of cleanups and drinking water treatment, monitoring of the environment, cooperate with the Czech Hydrometeorological Institute. We have established cooperation with Norway always now, talking about our Norwegian partners. So we cooperate with the COVID company specifically on various things concerning analyses of samples of the environment. So our circle of interest is quite wide and quite broad, and now I am going to present you a few results and pieces of information concerning the pollutant of the aquatic environment, so-called micropollutants. What these micropollutants are. These are substances of anthropogenous origin that enter the environment and exist in various compounds in nanograms, micrograms per liter, per kilogram, depending what we analyze. And mostly these are pharmaceutical residues and residues of like the disinfection means and other pollutants and pesticides also, and which are used in the agriculture. And because we personal care products, and because we use them every day, then end up in the environment usually, and the aquatic environment is impacted by wastewater treatment plant effluents, but also actual runoff water from industry and agriculture and industrial activities. Focusing on the main sources of contamination by extraneous contaminants, first of these resources is industry, industrial activities. Of course, the treatment of wastewater has improved, but there are accidents from time to time and some leakages, and we also have to deal with the past. Because in the past there used to be contamination of the environment by a whole number of substances persisting in the environment, the so-called persistent pollutants. And many of them now are the components of the aquatic system, and we have problems with them in fish meat, for example, like toxic metals like Ag, cadmium, lead, PCBs, dioxin, and many others. And they are limited by the laws. The concentration in fish meat, for example, have limits, and we can make comparisons on the basis of those concentrations with with other existential entities, which we can also use in evaluating the risks from contamination of the fish meat. This is just to show you the situation. Actually, in terms of exceeding the sanitary limits of those contaminants, we have problems mainly with mercury, and basically we have few locations that are burdened very much, like the Skalka near Cheb reservoirs, high concentration. Also shows what was here in the past. The reservoir was contaminated by industrial wastewater coming from Germany, and it's still there. The exceeding of sanitary limits also takes place in some other locations, especially impacting healthy species of fish, because the mercury is specific in actually making deposits in the muscles of fish, and its contamination grows in food chain and connected with the age of those species. So the predant fishes like trout, pikes, etc., there are quite important concentration there. Mostly consumed fish, species of fish like carp, it's okay because the anglers or fishermen catch the fish in contaminated areas, but they are actually stocked in actual pond conditions, and they end up in the actual areas for the fishermen, and then they come practically from not polluted environment of the fish ponds existing mainly in southern Bohemia. Another important source of contamination is agricultural activity. It's agriculture, which impacts the ecosystem in many ways due to the fact that they plant technical like substances like corn or maize, and so they can be burnt. There's soil erosion, deposition of gravel and sand, and so reproduction actually impacts the reproduction of fish that is tied to this gravel and sand, and the used substances are used. And there are so-called pesticides, which end up then, as a rule, in the aquatic environments. We have problems with contamination of surface and groundwaters, and it's not only the maternal compounds, but also and degrade somehow in that environment. And we concentrate on the metabolites, degradation products. We find out that they persist there for a very long time, and they exceed the set sanitary limits. And if you look at the presence of those substances, so basically the pesticides in surface waters of the Czech water in Czech Republic, it's a map of the Czech Hydrometeorological Institute now, so you can see the many red circles and orange colored circles, so tens of substances captured, and the size of the circle means indicates the concentration. Yet another source of contamination is municipal wastewater, in spite of being treated in wastewater treatment plants. So these plants are not designed to eliminate all the micropollutants present there, because the people use drugs, various chemicals, in households, etc. And these wastewater treatment plants eliminate something, and the number of those substances is not eliminated, and depends on the type of those substances. There's an enormous quantity of them. If you take a water sample about effluent and beyond the effluent of the wastewater treatment plant, practically 20,000 population, and if you do targeted screening in our machinery, you can see the different 50,000 compounds. So a great number of substances that actually leak, and we focus on a small part of them only, but it is a part of great significance. These pictures are the result of our long-term studies, when we actually monitored the efficiency of cleaning by the wastewater treatment and in České Budějovice the whole year, and the wastewater incidents of various substances which we monitored in our farms. So there are quite clear trends regarding elimination of those substances during the treatment process. So there are substances that are 100% eliminated, but there's some others that are not practically eliminated. Carbamazepine, which is anti-epileptic drug, and so some of those substances we don't see at the beginning, and then they release from them conjugations and concentrations behind the wastewater treatment plant are higher than before it. And then in antibiotics you can see trends like they are used in autumn, winter, spring season, so the concentrations are highest in those seasons. Antidepressive drugs, antidepressants, the same. And so from those studies we have information about what kind of substances penetrate in the environment, and how the wastewater treatment plants are efficient or not, and what penetrates to the aquatic systems. And among those sources that I've characterized a little bit, what actually the substances get in the environment, and kind of create a cocktail, a mix-up of those substances in water, which can impact the present aquatic organisms. And when we use that water, also going back, they can impact humans. And now we have also some questions. Which localities, what type types of localities these organisms are mostly impacted. Do you think will it be a small streams like under the town of Prachatice? You see the wastewater treatment effluent or Vltava River here behind Prague or beyond Prague. Yeah, we're talking about concentration, the final concentrations of the cocktail of substances which is there. A certain solution is dilution. If the dilution is sufficient and the concentration of that cocktail basically do not represent, according to what we know, do not represent an enormous risk. It's the example of the Vltava River beyond Prague. It's a big, municipal agglomeration, but then water is treated or cleaned through the Vltava cascade on the river. So, according to our knowledge, it doesn't represent an enormous risk, a significant risk. But these types of small locations where there is a small level dilution and the share of the treated actually effluents in the streams consisting 10 to 20% of the whole flow, we can see a number of negative effects. I'll show you a few maps looking at the big streams, water courses, concentration of pharmaceuticals. I think some 1993 compounds were measured there, so you can see the violet-colored circles. There's major streams are Bílina and the Svratka beyond the town of Brno, quite small streams, and beyond the city agglomerations. Otherwise, it's okay. But if we take a look at the small streams, you can see the violet circles are more frequent in west situations, those small streams where there is a low level of dilution of those substances actually released from the wastewater treatment plant. If we project this into such a chart and look at the smaller municipalities, like beyond the village, there is some stream coming from the forest. We can take the location above the village. We are somewhere here, then it actually flows through the village, and there's a small level of dilution after. So after in some hundreds kilometers, we can be Prague, Ostrava towns are relatively in the middle, but the worst situation prevails on the small streams that are impacted by insufficient dilution. So what kind of risk the pharmaceuticals represent in the environment? In general, the pharmaceuticals are not designed to be toxic, with the exception of few substances, but the presence of antibiotics residues in wastewater and in the environment leads to a resistance of those pathogens. And the presence of the water cocktail, actually induces chemical stress in those organisms, which actually is reflected in various physiological functions, histopathological changes of the exposed organisms. A group of those substances, like the hormones and similar substances, impact reproduction, the degree success of natural reproduction. They disturb the hormonal systems of those organisms. And then there's an important group of substances, anti-allergetics, drugs, for example, which are not toxic but change the behavior, have impact on the nerve system. So the flocks of some fish break down. They do not look for shelters to hide before predators. It disturbs. It's a change of behavior on their part. Those flocks of the fish or presence of the entities in those locations. So we have a map. We could see those charts. This is the specific situation in southern Bohemia on small streams, relatively small villages. We have Polary, Prachatice, Vimperk, Brloch, those municipalities. Relatively biggest is Prachatice, 11,000 population, and then smaller municipalities, thousands of inhabitants. And if we take a sample in a brook above the source, above the municipality, you can see there's a small circle, but beyond that, the circles are bigger because the concentration of those substances grows, and it's pharmaceuticals to actually combat the high blood pressure and some other actually pharmaceuticals that influence the nerve functions, nerve system functions. If you look at the organism and specifically fish and take samples above and beyond the source of contamination, and we can make also long-term studies, and we stock like marked fish in those streams. We know how long these species are exposed and take samples, and then with the help of the biomarkers or biochemical indicators which actually respond or react flexibly to sources of contamination, so we can observe a certain sort of feminization. When we do histological analysis, we can take actually analysis with spermatic samples in males. So we are talking now, these are the small balls. We talk about hermaphroditism, and then we have markers, the presence of substances with estrogenous effect, that is the male hormones in the aquatic environment in the males. We provide for so-called bitologyny, which is a substance produced by females. It's a stock substance in liver, and it deposits in liver, and they have it. The males also have it, but it's not infected. If there are higher concentration, these substances with estrogenic effects, so the males also activated, and so we know that this location is influenced by that substance. But there's some liver markers, detoxification, enzyme of the liver, chemical stress, and the actually the situation is the same in all similar locations above and or upstream and downstream of cities, and so downstream is always bigger. And we have interesting we confront our fishery approaches with toxicology, and we see the influence on early development stages where the species are most sensitive, like the common trout during incubation. Trout spends up to 7 months, depending on water temperature, because it spawns at end of October, the beginning of November, and the fish egg balls then go out at the beginning of April, and then it lies on the bottom of river streams for some time because there is fructification. So these are sensitive, and because they can also with regard to the fact that there are just single rainfalls, and so there is effluent from sewage systems, like the fine sludge accumulates all times and covers the whole bed of those streams, and the small egg balls lying there for half a year. So the chemical contamination is not substantial for them, but they are covered by that sludge, and they actually die out, and then there's a factor of temperature. The thermal contamination in wastewater treatment plant changes the whole ecosystem. Downstream, if you have 1 degree difference in winter time, so if it's 1 degree Celsius and 2 degrees Celsius downstream, so the development of the fish species is twice as fast, so it influences significantly the development of those species. And we can also the sexes influences the 1-to-1 in control locations, and downstream 1.8 to 1 in favor of the females species of fish. And we can observe accumulation of those substances in the fish organisms, and in the fish eggs, and also the fish, and we can see what the problem is with regard to accumulation. The big problems, as I said, are psychoactive substances, consumption of antidepressive substances ever increasing in the society, because the society is under pressure, in stress. So these substances come from the aquatic environment. So if we do monitoring of our rivers, we can see those psychoactive substances which you can find and measure are quite a lot, like pervitin, that's the red color. So actually the narcotic drugs are used by fish. So we could see that in a study. And thanks to several weeks of exposure, the concentration on the downstream part of the wastewater treatment plant actually evoke or elicit addiction of those fish. So the worst situation to salmonella with regard to concentration of the substances of the cocktail is in small locations where there is a small level dilution, and I call it so-called cocktail effect. The effects are combined. You can't model it in a laboratory, so it's in nature. It is as such, and after a lengthy time, there is some kind of change of those organisms, and in future we must definitely change our approaches in the field of agricultural management and development of new pharmaceutical technologies will be applied, reducing concentration of some substances, and which will be given by the law limits, and so of course those pharmaceuticals will be consumed more and more. But if I liquidate those substances, I should at least bring them to the pharmacy and not throw them to the toilet. And so the cleaning methods of drinking water and wastewater is improved and must be developed, and monitoring must be developed, from which we get information of the present problems that were to be improved. We need good equipment, good experts or people, efficient and sensitive broad spectrum analytical method which enable us to proceed further, to advance for the. I would like to thank you for your attention. I also wish to thank you. You are excellent. 20 minutes exactly sharp. I didn't say in the introduction, should you have any questions? So in the end of the session, there will be space for the questions, time for the questions. And in the beginning, I forgot to say to welcome our colleagues from the Norway Environmental Agency, Alliance, and others. I wish you a pleasant good day. And now, as I mentioned in the beginning, our colleague, Mrs. Fedorova, is ill. You can have a drink, you can have a rest, take a microphone, etc., etc. I'll try to convey this presentation to you somehow.
This presentation actually follows up on my presentation. This is about the pharmaceuticals and them getting into the aquatic environment, and also the potential of biological bonds in the removal of micropollutants from municipal wastewaters. It is, in some cases, it is necessary to install some kind of chemical device that would remove the micropollutants, of course. I will tell you at the beginning the main aspects, general aspects. Then we will focus on results of this type of experiments. We have one advantage: we connect fishery and toxicology, and we work with various organizations and towns. In our lab in Vodňany, we have a creek, Žižárka. and all water that fills this pond comes from this water treatment facility. We have been doing a lot of experiments there for many years, and we try to see how effective in this pond, how it works in the summer, in the winter, whether the micropollutants also get into fish, whether there is a risk of fish consumption in these locations. So we do sometimes 2-season experiments in this area. So I will share some results with you now. These are basic facts. My colleague Anya prepared this for you. So when it comes to water from the water treatment facilities, of course, some nutrients are also in the waters. They are eliminated. Also, the risk of pathogens is there, but they are eliminated mostly. There are many substances, however, get further into the aquatic environment. It may be metals, but mainly the pharmaceuticals and the chemicals, the personal care chemicals. Worldwide, the problem is water. Water is the basic strategic ingredient, and it is necessary to work with it very carefully, effectively, and try to maintain it. It is well known that the previous generations basically dried out, and they perished because they had no water. Their water management was so poor that they perished at the end. So it is necessary to really pay attention to water and have it as priority. In terms of water on Earth, 97% of water on Earth is in the form of salty water. In oceans, only 3% of water is fresh water, and out of these 3%, it's mainly icebergs and underground water, and 1% is a superficial water, the fresh water. I don't know if you know how many liters of water a person consumes on Earth in one day. What is the consumption? Do you have any estimates? I will tell you. It's about 3,400 or 5 liters. This is not only water for drinking, but water consumption in general. Here you can see various commodities and water that is used to grow 1 kilogram of the given commodity. So, for example, in case of coffee, for 1 kilo of coffee, it's almost 20,000 liters of water. So water sources in general are very limited, and a problem may come with water. Many countries have such a problem. For example, Israel, as you know, does total recycling. Everything that goes from households gets recycled in water treatment facilities. It is then used in farming, in aquaculture. So wastewater is not really a wastewater. It is actually a source of water in some cases later. Now I am getting to our experiments and our observations, which have been done on our ponds and facilities close to Vodňany. Vodňany town has 7,000 inhabitants, and there is water treatment facilities there that produces about 2,000 cubic meters per day. Then the water flows into the small pond. It has about 3 hectares, and the pond further purifies the water, and the water from this pond then goes into a big production pond that is used for breeding fish, especially carp. we, in this study that I will present, we focused on incidence of a broad spectrum of pharmaceuticals and their risk. One thing is measuring concentrations, and another thing is saying what it means, whether there is a risk for the organisms that live there. And of course, we also focus on bioaccumulation. That means how and if the substances gets stored in the fish. That means in the small pond and in the big pond. Here there is a map where you can see it. This is the purification pond, production pond, and then in the ponds we had more sampleries, places where we took samples at the effluent from the production pond, and also checkpoint location. When you do an exposition study, it is necessary to do these checks. Of course, there is no super clean location anywhere. You always measure something. So we used our experimental facility at Blanice River. So of course, the concentrations of substances are still there, but much lower than in the exposed locations. When we looked at the substances, in each substance, we could say how it is eliminated in the system of the biological tank. In the whole season, whether in the summer or winter, they actually were not eliminated. It is the example of the metabolite I was talking about before, the epoxycarbamazepine. I was talking about the antibiotics before. It doesn't matter whether it's winter, in the fall, their presence is common. And then there were substances that were easily removed, so their concentrations went down significantly in the ponds. Then there were combinations of seasonal incidents, and the degradation was mainly in summer months when also the microbiome of the pond plays a role, all the plants play a role, and it has an impact on the elimination and transformation of the substances that flow in the pond. Now, assessing the risks connected with presence of the substances in the water, the risks are quite complex. It is described in this publication. I won't go into details. However, for individual substances, we assess risks for water organisms. And when we calculate the risk factor, if it's over 1, then it represents a risk. Then there is a risk there. And we then work with the measured concentration or concentrations. And then we work with the predicted concentration, which does not yet induce any effect in the given form of organisms. It's usually from some database. When we prepared the results into charts, these lines are the individual locations. Specifically, the blue one is the production pond where the wastewater flew in. And as you can see, in case of venlafaxine, which is an antidepressant, there were lower concentrations in this season compared to the to another pond connected with the Blanice River. There is, of course, also some difference here with further in carbamazepine. You can see that the flowing through the first pond did not really have any impact on the concentrations in this case. You can see the predicted concentrations here that have no effect yet. For example, this interrupted line is fish. The dotted line are don't have the individual substances are compared annually. So in case of this drug used for hypertension, the concentrations that were identified there should not have any essential effect on the water or organisms. In terms of venlafaxine, which is the antidepressant, there is impact here on fish because it's about the change of behavior in the fish. And one parameter of the assessment is also the behavior of fish. So this is the way the substances were assessed. Most of them, at the minimum in the production pond, did not represent any significant risk for the organisms that lived there. The ecotoxicological risk, in fact, went down, and it is described that it goes down in the process of purification. So when it flows through the biological pond, it goes down, and then in the production pond, it goes down even further. Then I said that we also focused on presence of substances in the environment and whether it has impact on quality of the fish meat, whether these substances also get stored in the fish meat. So we did an annual exposition. We took species that are mostly in the ponds, that is carp, as a typical carp river, and then we took another fish we used was the zander, and we focused on a broad spectrum of drugs. It is published again if you need more detailed information. However, the important fact is that in the mussels, the concentration of the substances, the presence of these substances was minimum. The concentrations were lower. So from this point of view, there is definitely a potential here to use these biological ponds to purify the wastewaters. There is a potential here to use the water for other purposes, including aquaculture. For example, we also do experiments with irrigation using sludge from water treatment facilities. We also cooperate with the Czech University of Life Sciences with Professor Kodešová. So we do a lot of experiments, and it is necessary to look at it and assess the risks so that we don't have more problems in the future. In terms of the hygienic quality, so-called perfluorinated substances in fish meat, EU has set a new limit at the end of 2022, and now we can see that the concentrations in the fish are quite problematic because the limit is very strict, and it is set up for different kinds of fish differently. Carp has 2 microgram per kilogram, and other fish have different values. This is given in legislation, so we have to look into this more because there is a risk that in some locations these limits will be exceeded. These are the perfluorinated substances are used quite often. You probably not many people know what these substances are, but it's part of your clothes, like Teflon, Gore-Tex, all of these impervious textiles. It's part of furniture, of carpets, on frying pans. There are Teflon layers. So all of this may cause us problems later because when these substances get into the water environment. Thank you for your attention.
Vaše dotazy tedy
So your questions will come after we finish this session, and we continue in the pharmaceuticals in drinking water in the Karani water treatment plant. Representatives of the Tomáš Garrigue Masaryk Water Research Institute representatives is coming to the podium to make their presentations. Wish you a pleasant good morning. Ladies and gentlemen, we have heard an interesting lecture on fish, and the fact that the fish contain various substances which should not be there is sad. But what is much worse is if these substances are in drinking water, because I'm in the PSA sign born actually, so I do not drink water, but the water which we have to the water they have to drink is quite topic, and the story of pharmaceuticals is the topic of my presentation. I was introduced. I represent the Water Research Institute here, which has been dealing with this subject for quite a long time, and we're going to talk about the Karani water supply works, which actually delivers about 1/3 of consumption water to Prague, and it's one of the most significant sources of drinking water in Czech Republic. And it's really a unique technological set using two technologies. Both are historical. The first one comes from 1906 to 1913, from those years. It represents a set of several hundreds of drill bores along the Jezera River, which transform the surface water into groundwater, and this process is called bank infiltration, and this technology was supplemented in 1961 by a second one, which is called artificial infiltration, and which does the same, that is transforming the surface Jezera River water into groundwater, but in a different manner. There is actually pumping out in the Sojovice weir, pumping out that water in Sojovice weir, and thanks to big equipment, actually 500 meters long, actually absorb that water to underground and eliminate the various harmful substances in it, and create water which was considered for one of the most best quality waters which we had in the Czech Republic. But we focused on monitoring of those substances, that is pharmaceuticals, PPCP substances. Nevertheless, we laid the biggest emphasis on those pharmaceuticals. The first step we did was to look at the concentrations of those harmful substances in river water. That is the raw water from which the Karani water supply works produce drinking water. What you see in front of you is the result in the field of the town of Mladá Boleslav. Mladá Boleslav is about 40 kilometers upstream the Karani location. It's a city agglomeration with 40,000 in population, with a well-known industrial activities. There is the Škoda car maker, Mladá Boleslav. And what is most important, they actually tribute to a common municipal wastewater treatment plant behind the psychiatrical ward or psychiatrical hospital in Kosmonosy, which delivers to the wastewater treatment plant and subsequently to drinking water a wide range of pharmaceuticals. So this is actually no surprise for the citizen in Sojovice. That's the weir from which the water comes, the raw water comes, used for the production of drinking water in the Karani. And so it contains about 36 substances of PPCP category, and most of them are substances from the in the pharmaceuticals category. You can see a survey, kind of overview. You can see that it's a quite a versatile group. Nevertheless, you don't need to be astonished that the Isra River actually would be some exceptional water course, because in parallel to this monitoring, we did also a European project which monitors using identical methods the contents of pharmaceuticals in several water supply courses in Central Europe, and specifically the Elbe River in Dresden, Ezar, Jizera, Italian part, Sava and Prinica. And when after 2 years of monitoring we made a comparison, we stated, or we noted that the concentrations that we had measures were more or less identical in all water courses. So this is no surprise, because all Europeans are roughly equally ill and treated in a similar manner. And so what actually comes from them to water courses, those substances are very similar. And if a comparison here, the red field substances that appeared in all water courses, the orange field group of substances that from time to time, in one case specifically in Brnica, which actually was a simplification, but most important field is the red one. These are substances, I dare say, if we take some samples from any watercourse in Central Europe, and I even dare say that this would actually apply to the whole of Europe, so we can practically rest assured that these substances in the red category will be found just everywhere. So it's in quote unquote natural background, because if we want to be sure that really in samples of surface water something is missing, we would have to actually travel to some spring areas upstream the first wastewater treatment plant, because even below that we can find those substances in surface water. Metformin is most interesting, maybe in big quantities, practically everywhere you can find it, and it's a substance to cure metformin. This is quite a relatively cheap substance, so they are administered in high doses to patients, because every fifth citizen of the Czech Republic, and I dare say it's the situation prevailing in the whole of Europe, people suffering from this disease. So there's not much surprise that metformin it can be found in such concentrations. So let's have a look at substances that actually flow from the wastewater treatment plant in Mladá Boleslav. And we can say that the wastewater treatment plant in Mladá Boleslav cannot be blamed for anything, because it works practically in harmony with the existing laws and regulations, using technologies that are adequate. In spite of that, what actually flows from them, and that's the reason also the psychiatric hospital in Kosmoletsko actually sending water there. So then what comes from that is the cocktail of pharmaceuticals and personal substances, personal consumption substances. It documents the wide scale, the first chart. I focus rather on the two ones, because in terms of the first one we have tens of hundreds of nanograms. So the four substances, tramadol, diclofenac, lamotrigine, and hydrochloric azethine, are substances used for as painkillers, anti-inflammatory substances, diuretics, and anti-epileptics. So we are getting to concentrations in thousands of nanograms. We are getting to micrograms here, and the biggest problem of Jezera river oxyplonil dalmisazen, medicaments used for heart diseases, for treatment of heart diseases, which appear here in tens of thousands of nanograms here. So this is basically a substance cocktail that actually flows to river water. Fortunately, the reservoir dilutes significantly those wastewater from the wastewater treatment plant. As you could see in the Soviet example, there are still quite significant concentrations left. There was a very interesting slide we could see in the previous presentation, which showed certain seasonal cause of pharmaceuticals in waters. And we focused on daily courses or 24-hour intervals, and you have the result. It's again in the Jezera water, and there can be carbamazepine or metoprolol, and it doesn't matter if you take them during the daytime or nighttime, because these are substances that from medical point of view tend to release gradually in human body in such a manner so there is some lasting level, and so there's no peak quantity or peak concentration. On the other hand, you have ibuprofen substances of the type which you actually take if you have some pain, and the purpose is to respond immediately and to create to release the effective substance quickly. And then we have caffeine type of substances, which doesn't fall under the category of medicaments or pharmaceuticals, but rather those substances of personal consumption, and this is dependence on human habits. You have a cup of coffee in the morning, then you have one more cup of coffee after lunch, and then people who are very dependent on that. And there is one important dependency here. It's very important conclusion for monitoring purposes. It's necessary to do monitoring at a specific hour, which will be constant, which will be unchangeable. Otherwise, we might actually introduce systematic errors in that. So now we are getting to drinking water. We monitored the bank infiltration. We didn't find any basic problems. There's always some medical substance with concentrations only of tens of nanograms, but no pharmaceutical appears systematically in drinking water and in that water. And so the explanation is quite logical. We have a natural barrier. There is the colmatation layer of the river that has developed for hundreds of years here. There is clay minerals with high absorption capacity, most of all, and they effectively eliminate the pharmaceuticals leaking from the river to the gravel sediments around. And so this barrier works highly probably very well, and the bank infiltration, we can say, is without problems. Much worse situation with the artificial infiltration, because the river water here is actually absorbed in tubes with gravel material. The sorption actually practically doesn't work here, no other material contained, and the water gets directly in the gravel collector with minimum sorption capacity. So these mechanisms do not work here, and we found out that relatively versatile group of pharmaceuticals which we have in surface water after it is absorbed, and we do the monitoring of drinking water. So it does not respond on the process of treatment, so it reduces the concentration, but it's a quite a broad scale or quantity of the substances gets also in drinking water. In the first stage of monitoring, we used all that system as a black box. We measured concentrations of in river water, which was infiltrated in the sorption tube or basin, and so then we let the water stream to the actually capturing reservoir, and we follow the concentration. That is what happens with those substances. So we are basically not interested in the process on attenuation on the track which happens there. In the second step, between the infiltration track and the clarifier, we made 2 drills trying to find out what happens about the pharmaceuticals which are absorbed in the infiltration pond. So on the route to the actually clarifier. And so let me make a note. The first group of substances represents substances that we infiltrated in the absorption tube or basin. There is substances in the water, and before the water reached, after some 60 meters, before it reached the monitoring drill HV1, it disappeared. I don't want to say actually disappeared because it got under the detection limit. We must be very careful in using the term of disappeared, because in a number of cases those substances can be transported to subsidiary or daughter projects. We are able to detect some and not some others. So we must be really very careful about the terminology which we use. So other substances disappear, quote unquote, after the flow of, let's say, 90 meters. But another group of substances gets even to the capturing pond, and if we compare the original concentration, the concentration which we measure in water, which gets in the drinking water lines or mains, we can find a quite versatile efficiency of elimination. There are substances like metformin which will remain true but decrease significantly. But when we make such a comparison, we have substances that are partly eliminated, but the effectiveness actually drops significantly. And last group of substances are those creating the biggest problems. There are 5 substances for which the natural attenuation of the environment does not respond. It goes through the actual rocks environment, and the concentration remains the same. Like in the raw water, these are substances that get into the water lines or water mains. So now it brings me to a conclusion. Monitoring has indicated that the rocks environment has a very good attenuation capability. Nevertheless, small groups of substances does not respond to natural attenuation remaining in drinking water. And now the question is what to do about this. So you're in a situation that there are more than one substances present in drinking water, which is always the case. And I've used again the term of cocktail, which is very expressive, really. But it's not possible to predict the health risks of those contaminants, because they can function independently of each other or extremely also in synergy. The contents of the detected substances are those remaining remaining in drinking water are extremely low. Really, you could see that we actually deal with concentrations of tens of nanograms. So specialized literature agrees generally that this is not a phenomenon that would directly threaten human health. So I'm talking about substances from which I would single out only antibiotics, because most of the doctors actually are reluctant to say anything about that. We don't know anything fundamental, because there's no clinical study that would prove the effects. So we know from the previous lecture that we have explored in detail the impact of pharmaceuticals on fish population. Something like that does not exist in relation to human health, because such clinical study is not possible. We do not have a testing sample of people who would drink water for a long time without any pharmaceuticals. We would have to take tens of thousands of Amazon River Indians where we could be sure they are pharmaceutical free, and test them in the middle of Europe somewhere. There's no such study, but basically such a study would not be indicative, because there is an important fact is we can't single it out of a broader context, because we are getting the pharmaceuticals in our bodies not only in the form of drinking water, but also through some other processes, and it's in meat, fruits, vegetables, and singling out just the drinking water for the broader context is not possible. So in conclusion, I note, yes, basically in drinking water not treated with the use of the technologies about which we will learn more, definitely the technologies based on activated carbon, which really liquidate pharmaceuticals in drinking water. So we must actually reconcile with the fact that pharmaceuticals are in drinking water but low concentration, and the question is really that we do not know what to do about that. Thank you very much. And since this presentation was about pharmaceuticals in drinking water, so the next topic are pharmaceuticals in surface water of the Vltava River, and I invite the head of the laboratories of the state enterprise of the Povodí Vltavy, Mr. Marek Liška. Wish you a good morning.
Dobrý den, dámy a pánové.
Good morning, ladies and gentlemen. I will try to follow up. If you have a feeling that we are saying the same thing with Mr. Randak, it is partially true only. You will see that when two say the same thing, it's not exactly the same thing. I'm here from the state enterprise, the Vltava River catchment. From the laboratories, we do monitoring of surface waters, and there is aquatic law and legislation governing this. This is just for your idea of what monitoring means. This is the Vltava River catchment divided into 3 areas. We monitor approximately 350 water bodies. We have profiles on flowing waters, standing waters. The monitoring is done once a month, and part of the monitoring is also monitoring of wastewaters of the significant polluters. There are quite many of them, and about 40 of them we do also monitoring for pharmaceuticals. These are the main groups of pharmaceuticals. You saw something similar in Mr. Randak's presentation. These are about the same therapeutic groups, from analgetics to antibiotics, pharmaceuticals, contrast substances, and other substances like industrial additives, benzotriazoles, and other ones we already talked about today. As I said before, we have 3 laboratories. We analyze these substances in our lab. We use liquid chromatography with weight detection. And this chart illustrates in a way development of analyzed substances. It is similar in case of pesticides when the problem seems to be present only now, but it has been there for a while. We have, thanks to Norway grants, we will probably be able to extend this list even more and get to lower levels of detection. You can see that in the year 2010, we analyzed about 7 substances. Nowadays, we have about 130 of them, including some selected metabolites. The main engine of the pharmaceuticals circulating in the nature is a man, are we people. Before the people came and started to synthesize the pharmaceuticals, they had not been in the underground or surface waters. The main source, of course, is human urine, and also liquidation of unused pharmaceuticals flushed in toilets, for example, or just they are thrown in communal waste. You saw a similar chart before. This chart illustrates the highest concentrations of pharmaceuticals in wastewaters. We chose 4 wastewater treatment facilities, from the biggest ones to the small ones: Prague, Plzeň, Český Krumlov, Pelhřimov. You can see the pharmaceuticals here, or substances in higher concentrations than 1,000 nanograms. There's mainly oxypurinol, then telmisartan for high tension, then some for diabetes, hydrochlorothiazide for hypertension, and other substances, iopramid, and then also sweeteners. And this is where the concentration 1,000 nanograms ends, and this is where higher concentrations start. So you can see that there are quite big concentrations in the wastewaters of these substances. Now about 5 such diagrams will follow, or concentration maps, let's say, with concentrations of selected substances in wastewaters. Unfortunately, we have not multiplied the flow rates and concentrations. That's the concentration view, but there is another view which promotes, it is promoted by the Department of Water Protection in Vodňany. And we should see how organisms respond by their biological response. In some cases, concentrations are high, but they don't cause anything. Sometimes it's just the opposite. Here, in case of metformin, which is an active ingredient in a drug treating diabetes, daily doses in patients that patients use are quite high. It's 1.5 to 1.7 grams per patient. So it is quite a big burden then. It's about 250 tons of metformin for the whole country. And you can see that the concentrations leaving the individual treatment plants are micrograms per liter. In micrograms per liter, those are usually the municipal wastewater facilities, or for hospital wastewater treatment facilities. or another one in Prachatice. There's a hospital there too. And they flow into a small stream there. And there are two more wastewater treatment facilities. It's a rehab institute in Kladruby and a hospital in Pleš, two hospitals, in fact. Another substance which is quite significant is gabapentin. It is used for neuropathic pain treatment because it gets all the way into the brain through all the barriers and is used also for treatment of epilepsy. Here you can see quite high concentrations, 30 micrograms per liter in wastewater. At the rehabilitation hospital in Kladruby, they have about 250 beds there for patients, and the patients use this medication a lot, as you can see. Nowadays, we also cooperate with some doctors. They say that prescriptions of gabapentin has been going down. It has been substituted by pregabalin. We started to analyze it this year, so we will see where the results will move further. Another substance, there will be two of them now. Those are not pharmaceuticals. Those are X-ray diagnostic. It's Yopromid. In this case, you can see high concentrations from Tábor Hospital, for example, the wastewater treatment facilities in Klokoty, Havlíčkův Brod, and Prachatice. Again, concentrations 15 to 30 micrograms in liters in a liter of wastewater. And another X-ray diagnostic is Yomeprol. You can see highest concentrations leaving. Average concentration is in a hospital in Pleš, Níšek pod Brdy. However, the Rehabilitation Institute in Kladruby does not use this method for the X-ray diagnostics at all. That's why the concentrations are low. It also depends very much on the individual hospitals using this substance as the X-ray diagnosticum for these diseases. Telmisartan has already been mentioned here today. It is quite a drug quite often prescribed for hypertension. You can see that the concentrations are quite even out in the whole territory and quite high in micrograms per liter. The last substance in wastewater, which represents the artificial sweeteners, is sucralose. And you can see that its consumption is really going up. It is becoming more popular. It is an artificial sweetener. It is 300 times or 1,000 times sweeter than regular sugar. It is used because it has almost no calories. It is used by diabetics in reduction diets, and it is used as substitute for sugar in various beverages that are consumed a lot nowadays. So we can say that wastewaters basically are becoming sweeter as surface waters as well. The concentrations are quite high. You can see that, for example, from this hospital, there's 50 micrograms in liter, and from wastewater facilities, the numbers are much lower in the case of sucralose. We are interested in the way the water treatment facilities work. We have a model example in Klatovy. It is close to Pilsen in the Czech Republic. And this water treatment facilities flows into a stream, then that flows to Uhlava. It's a town with about 250,000 people, and when the water flows into the wastewater treatment facility, Yearly, there's about 1,353 kilos of pharmaceuticals and the inflow and the outflow about 200 kilos. So you can see the ratio is about 1:5 or 1:6 when it comes to efficiency. It is wastewater treatment facility without the active carbon, so it is actually quite successful. You can see the difference in inflow and outflow. For example, metformin can be disposed of quite easily. However, other substances are harder to eliminate, as you can see. In the past few years, we have also been doing analysis of addictive substances, usually illegal drugs. In our portfolio, we have about 20 of them, and when it comes to the significant concentrations, it's mainly methamphetamine that we measure, which is the active ingredient in pervitin, we also then measure the presence of these substances in Klatov wastewater treatment facility. We already mentioned the biological ponds, which is quite frequently used facility. And here in this chart, you can see that we use quite often wastewaters from Pelhřimov, because it is a town of 16,000 inhabitants, and the wastewaters flow into Biela River that goes to Želivka River, and Švihov Reservoir then supplies water with for about 1.5 million people in the Czech Republic. So we focus on that quite a lot. And from this chart, you can see that in all substances, we can see a clear drop when we compare the inflow and outflow after those two biological ponds. Only in case of metformin, when the level goes down in the wastewater treatment facilities and then goes into those two biological ponds. After those two biological ponds, the drop is not so significant anymore. Now we are getting to the surface waters. There is only one map here as an example for metformin. It has already been mentioned here before that the bigger the town and the smaller the stream, the higher the concentrations. So we have stream Příbram, Prachatice, Slaný, Zákolanský, stream in Kralupy. It has already been said. There will be 3 slides here showing the difference between a small stream and a big stream. We have picked a few substances we have been measuring long term where we can already see some patterns. For example, in case of diclofenac, that is used as anti-rheumatic drug or anti-inflammatory drug. The concentration is about 400 or 500 nanograms in liter in the streams. In gabapentin, 600. Gabapentin 600 nanograms per liter, and for the hypertension, in hypertension drugs, it is 1,000 nanograms per liter. It is surface water where fish live, you have to realize, so the concentrations are quite high. In this chart, you can see that sucralose is really getting more and more popular lately. Here, we got from the higher, smaller streams to a place where Vltava River flows into Elbe River. That's the end profile of Vltava River, where the flow rate is on average 70 cubic meters. That means that all of these concentrations that are in 1 liter of water must be multiplied by 70,000 liters. And if that was then recalculated into us, then it would be quite a lot, even though the concentrations are already lower here than in the small streams. You can see that gabapentin, for example, here is at 200 nanograms per liter, metformin 500 nanograms per liter. So these drops probably are not caused by the fact that less substances would be used, but in the past 2 years we had much more water than in the previous years. But since 2015 to 2018, there was a significant drought in this country. I'm not saying it is so significantly better now, but we had definitely had more rainfalls in the past few years. On this slide, you can see the concentrations of a few main substances in water supply reservoir Švihov on Želivka River before taking water for the wastewater treatment facility in Hulice. Here metformin is about 350 nanometers per liter. Telmisartan about 30. It is much less than in the streams. However, this is a source main source of drinkable water, so it is still quite serious information. And now I'm getting already to the end. This is analytical set we have in our laboratories in Pilsen. We were able to get it thanks to the Norway Grants. When we got funds to purchase the liquid chromatograph LCMS, we should have a possibility now to lower the detection limits in the selected substances. And we should also be able to analyze untargeted screening in some samples so that we identify more substances. Besides this lab set, we bought a pre-concentration unit, Freestyle Xana, which can detect in a very sensitive way without the leakage of the analytes, can work with the sample about 1,000 times. So we get a very concentrated sample, and the measurements then are much more sensitive. Now I'm getting to the end. A lot has already been said. Which substances are most common in wastewaters that leave the hospitals? Which substances are in high concentrations? However, what has not been said yet fully is the fact that we have to do something about it. The substances in surface waters, as you heard in the previous presentation, also in drinkable waters, are quite many. And let's say 100 years ago, there were definitely fewer of them. So the man really takes a big part in the pollution, and the problem will grow further. Besides the fact we will have to use active carbon where there's a lot of ballast water. It will be very expensive. In some hotspot sources like the hospitals, it would be necessary to have some technological equipment for separation of these substances, or in some cases in patients who have the urine bags, for example, who use a lot of medication, or, for example, at intensive care units, we should collect the urine in such a way so that it doesn't get into the sewage system at all. We should dispose of it in a different way. Then in the topic applications, in the gels, in the creams, we should use some measures, take some measures. So when for example, the staff should wash their clean their hands first in towels before washing their hands in a sink, as an example. So that's all for me. Thank you. Thank you very much. And now, according to our agenda, Berta Roubcová was supposed to be the next speaker. She apologized for a personal reason. However, we will see her presentation now in a form of a video. This is the innovative innovative carbon-based sorbents as an efficient way of water for treatment. Technical University of Ostrava, Petra Roubcová.
Báze uhlíka.
This is innovative sorbents based on carbon. This is the video and financial support. There are captions, there are subtitles. Okay.
Metabolitov, patogénov či génov rezistencie a tiež mikro- a nanoplastov. Takto komplexne dočistená odpadová voda je využiteľná v poľnohospodárstve vo forme závlah. Vo videu postupne uvidíte laboratórne testovanie odpadových vod pred a po úprave čistiacou jednotkou, výrobu a testovanie sorbentov na báze uhlíka, samotnú čistiacu jednotku a následne aj pestovanie rastlín zavlažovaných dočistenou vodou.
Dnes sme sa zaoberali meraním základných analýz, a to konkrétne meraním HSK, čo je chemická spotreba kyslíka. Pri stanovení chemickej spotreby kyslíka sa koncentrácia organických látok vo vode posudzuje podľa množstva oxidačného činidla, ktoré sa za určitých podmienok spotrebuje na ich oxidáciu. Ďalej sme v odpadovej vode stanovovali množstvo dusičnanov, amoniakálneho dusíka a fosforečnanov. Sledovaním týchto základných parametrov možno posúdiť mieru vyčistenia odpadových vôd pomocou rôznych spôsobov, napríklad adsorpciou organických látok a makronutrientov na sorbenty, akým je napríklad biochár.
Vo vzorkách vôd sa analyzujú patogénne baktérie s ohľadom na Escherichia coli. Monitoruje sa celkový počet týchto baktérií a výskyt baktérií rezistentných voči vybraným antibiotikám, ako aj prítomnosť génov rezistencie. Sleduje sa ich odstránenie pred a po úprave vzorky vody.
Biochár je forma materiálu s vysokým obsahom uhlíka, ktorá vznikla tepelnou úpravou biomasy v inertnom prostredí, teda pyrolízou.
V našich laboratóriách vyrábame rôzne typy sorbentov na báze uhlíka, hlavne biochár, grafitický nitrit uhlíka a ich modifikácie, a následne testujeme ich mechanickú, chemickú a fyzikálnu kvalitu a tiež schopnosť týchto sorbentov odstraňovať liečivá a drogy z vôd. V našom projekte sú následne takto testované sorbenty použité priamo v kolóne umiestnenej v poloprevádzkovej jednotke na čistiarni v Ostrave.
Vítajte na čistiarni odpadových vôd v Ostrave, kde máme takúto krásnu ultrafiltráciu v kontajnerovom prevedení, ktorá si čerpá vodu z Zímky, kde máme uložené ponorkové čerpadlo, takže voda, ktorá už prebehla čistením na čistiarni, sa čerpá s ponorkovým čerpadlom a ide to do nášho lodného kontajnera, kde sa nachádza ultrafiltrácia. Nachádzame sa pred vstupom do kontajnera, kde máme ultrafiltráciu, takže poďme sa na to pozrieť. Na úvod z toho dávkovacieho, z toho ponorkového čerpadla sa čerpe voda do prvej časti nádrže, to je N1, ktorá tam slúži ako taký balans a od toho si vlastne pomocou odstredivého čerpadla tlačí vodu cez automatický spread filter. A takto predfiltrovaná voda nám ide cez zákalomér, rôzne čidlá, prietokomer a vstupuje nám to na membránu ultrafiltračnú z dutých vlákien, ktoré sú vnútri, ich nevidíme. Ultrafiltra z membrány sa potom čistí ďalej na sorpčnom materiáli. A takto vyčistená voda sa nám zbiera v druhej nádrži N2 a tá slúži jednak už ako zásobáreň čistej vody na spätné čistenie, alebo potom sa nám sústavou pneumatických ventilov prepnú automaticky a vyrába nám jednotka vodu. Okrem toho samozrejme máme tu nejaké čistiace chemikálie, čiže raz za čas jednotka sa chemicky vyčistí. Tu sa nachádza riadiaci panel, z ktorého vieme ovládať, vidíme všetky aktuálne parametre, vidíme to graficky znázornené, tak napríklad máme tú nádrž prvú naplnenú na 80% a vyrába nám do tej druhej nádrži a aktuálne máme 31%. Čerpadlo, to prvé, nám funguje teraz zapojené na 30%, filtruje, prebieha to sústavou ďalej. Máme tu rôzne režimy, teraz nám prebieha automatický režim, čiže jednotka si všetko riadi sama.
V rámci projektu ISBU inovativní sorbenty na bázi uhlíku jako účinný způsob dočišťování odpadních vod byla nasazena zahrádka, kde bude prokázána sorpční účinnost čistící jednotky vyvinuté v tomto projektu. V rámci experimentu bude stanoven průnik farmak do rostlin, rukola, řeřicha a salát u jednotlivých sorbentů na odebraných vodách z čistírny odpadních vod. V rámci projektu byly odebrány odpadní vody po procesu čištění pomocí naší čistící jednotky. Vody byly testovány semichronickým testem ekotoxicity na semenech Synapis alba, hořčice bílá. Testy prokáží, jestli je odpadní voda po procesu čištění ekotoxická či nikoliv. Pro ověření validity testu byla semena dověřena pomocí standardu dichromanu draselného.
Že to bylo také trošku filmového umění. Děkuji. Ano. I pod...
I wish to thank you. Even applause for the video is okay. So now, question and answers, please. Please, Mr. Randak, Mr. Harka, Mr. Rishka, please go back to the podium after your presentation now, because there will be questions. There may be questions. don't be don't be ashamed of that. You can stand. And now to the podium. If you have questions, the audience can raise questions, and ideally you should also say which of the gentlemen the question would be addressed to. So any such question? Ledere, Technical Analysis Liberec, good morning. Mr. Randak, we saw the situation in the about the surface water from as you see. What is the biggest problem with regard to toxicity about the pharmaceuticals? You can't say it's about the cocktail. It's not just pharmaceuticals. We have not mentioned pesticides here. And in my opinion, the pesticides will have still bigger impacts. You see the situation today with insects. Insects are collapsing today, actually, in a number of locations. If you look at the river bottom, there's a minimum quantity of insect species there, and what may play a role in this are also these substances. So you cannot relate this just to one particular substance, but we are talking about the cocktail. Otherwise, the testing of the different substances, it's difficult to say which of them are better, which of them are worse. But in general, it's about a cocktail of substances as such. So if I can add, the only solution which makes sense is the elimination of those substances in general. Yes, if I get the point. Yes, of course, it's difficult to eliminate. It will be very much demanding in terms of money. We can treat drinking water today, at least in the big water sources, in the big wastewater treatment plants. They have technologies of filtration equipment which are economically affordable. It will be reflected in the price of drinking water, but it's not some fundamental way of treatment of water. And water, with regard to the micropollutants, is okay. Then, of course, there are smaller sources of water, like wells, smaller water reservoirs. If there are agricultural areas, it's a problem not only with pharmaceuticals, but also pesticides. And perhaps some future technological solution may be to have smaller equipments like water supply reservoirs, like connected with taps directly, and a number of other things that have to be followed. And wastewater treatment plants, of course, it's not economically affordable to install them in all the factories so that the substances can be eliminated. There is the concentration of those substances in treated wastewater is much higher than in the sources of drinking water. So it's about capacity of the filters, frequency of change in the filters. It's not economically bearable to do it, in general. So we should set priorities on the wastewater treatment plants, like managing for governing factors, biotesting, which can be used to set priorities and say where to start resolving the most urgent ones, and then go further and further. Our society is not prepared at this time to make investments, such investments in, let's say, general water treatment measures. Of course, and then it's a question of agriculture. What happens today in agriculture? Well, it's not sustainable agriculture or farming, not what to generalize, but in the major part, the areas in communism, the areas were put together, biodiversity dropping, big fields, too big fields, repeated like maize, like seeding, etc. And they actually burn it like as biosubstance. They take it to Germany and back, and so then there's a problem, and pesticides in great quantities, etc. So here there is a huge problem with regard to biodiversity and contamination of water sources by those substances, and this needs to be resolved. Yeah, very extensive, pessimistic answer this has been. One question here in the front. Good morning. I have a question to Mr. Liška. Plus, you mentioned that with regards to the fact that hospitals and wards are the biggest sources of contamination by pharmaceuticals, and there are quite simple preventive measures that can be taken. Do you know about some campaign? Who is supposed to coordinate that? Who should be the leader of making those measures so that the healthcare personnel washes hands, etc., catch the urine, etc., capture the urine, etc., so etc. But I don't think it's that much easy. It's very specific because there are some medicaments coming from the hospitals, and then there are pharmaceuticals where this makes no change, like X-ray diagnosing specific substances used mostly by hospitals. But in general, concentration from hospitals is higher because patients suffering from diabetes and patients suffering from the mobile apparatus. So part of them may have diabetes, part of them may have been treated with some other medicaments. So those who are in like rehabilitation facility and doesn't have it only after accident situation takes many actual medicaments. So we can say that about those medical facilities, what comes from them is a very broad mixture of those substances, and one possibility is to complement them in some other where it is wherever it is technologically possible, like my colleague says, the cleaning, the treatment at some technological stages. From hospital there is no they are not affluent in municipal sewage system, and the municipality has its own wastewater treatment plant, like in the town of Klatovy, where we have these cases. And second part of your question, are there any easy solutions or simple solutions? I think that those solutions we have today are actually none. There's some campaign in pharmacies, please return medicaments to pharmacy, do not flush them in toilets, etc. And this is where it starts and this is where it ends, I think. And a certain possibility so that there should not be, there's not necessary treatment solution at the end. Nothing like that. Logistically, it cannot be actually managed easily in the treatment facilities and hospitals. Of course, the sanitary securing has connections, consequences. The urine bags should be collected, or perhaps the application of gels and balms can have, ointment has some regime. So we were in Geneva on the other day in such a conference, which we have not seen here so far, representatives of municipalities, water economists, pharmaceutical companies, and doctors attended. And the conference of this group of people was trying to find some solution, and some project was presented. There were a municipality, big medical establishment or facility, and they did monitoring of wastewater and some corrective measures, like prescription of medicaments, environmentally degradable medicaments are prescribed for high blood pressure. There was some chart, amlodipine, famotidine relationship. So there are possibilities, but you have to try to find them, and it's quite laborious effort. I can't describe them. I'm a biologist, a water economist, so I don't know. But we know that there must be some opportunities. Was there any output from that conference? Yes, they had a project showing some of those solutions because it included also some other countries. Thank you. Ladies and gentlemen, any other questions? Mr. Lederer? I must express myself about the situation of hospitals. I'm very pessimistic about the contribution from the Prague Tomayer Hospital, where the cleanup was completed, but as an exception, there are many regional hospitals which have no wastewater treatment plants or do have them perhaps in desolate conditions. So it's up to the Ministry for the Environment to do something about it. But the situation is not good. The only duty of hospitals is to make sanitation of water from infection department and pathology department. So it's all. These sources, I'm in favor. These are not they are not most significant, but with regard to research, they are general sources of contamination, wastewater, and sources to cure that situation. It's about investments in medical establishment. Thank you very much. Ladies and gentlemen, any other questions to the speakers in the first session today? Any wishes perhaps you can express? No? Nothing? Okay, gentlemen, in that case, I thank you very much for speaking during the first session. And we offer, ladies and gentlemen, to you a 20-minute coffee break. And we'll resume at 11:25. And so please use the terrace, have a snack, and do some networking to make acquaintances if you do not happen to know some of your colleagues. Thank you very much. všichni rychle, tak ono se to nějak v posledních letech jakoby u nás tak nějak ustálo. Přijednání třeba je to tak, že někdo se bojí, že ho přeruší, skočí do toho, že a nedopoví se ale taky někdy mluví lidi, a teď nemluvím o moderátorech nebo tak, ale řekněme vystupujících někde, tak oni tím naspívají podle mě i to, že se neumějí kvalitně vyjadřovat, že nemají přednes, tak to mluví exaktně a pregnantně vyjádřit. Takže oni začnou zleva, vprava, backhand, forehand, a teď to nevidí, kde skončí, a v té rychlosti v tom letí se to jakoby ztratí.
Dámy a pánové, budeme přibližně za 3 minuty pokračovat, to znamená, že pokud mě slyšíte, tak vás zvu opět zpátky k vašim stolům. Pokud mě neslyšíte, tak samozřejmě přijít nemůžete, ale já na tu terasu ven dojdu osobně. Takže drahé dámy, milí pánové,
So, ladies and gentlemen, I hope that you have refreshed yourselves, that you have absorbed a little bit the D vitamin, and you have washed away some, let's say, inauspicious or unfriendly first session content, like we agreed with our colleagues when we could see that much yesterday, that could be improved. So the first session about water contamination has not ushered too much optimism, and we hope that we will have some optimism during the second session. So allow me to invite the first speaker, the lady speaking, which on behalf of the Norwegian Environmental Agency will be Mr. Grant Nilund.
Dobrý den. Hello, everybody. Thank you for the invitation. I'm very happy to be here. I appreciate the project presentations in this conference, and also the nice conference facilities and your hospitality. My name is Ragnhild Nyland, and I live on the islands of Lofoten in the northern Norway. So I live above the Arctic Circle in what we call the land of the midnight sun. I work at the Norwegian Environment Agency, and I've been working on marine litter as an environmental issue since 2018. I'm going to present our ongoing work on monitoring microplastics and the interactive digital cleanup and data collection tool, Rent Hav, both being parts of our efforts on prevention and mitigation of marine litter and plastic pollution in Norway. Microplastic pollution is a major environmental issue. Microplastics are tiny plastic particles that, for instance, come from manufacturing of consumer goods and the degradation of larger plastic items. Our monitoring program for microplastics started in 2021. The image shows the locations where we collect samples from water and air. For those of you particularly interested in the setup of the program and the results, I encourage you to read the reports, which are available in English. Micronor is a knowledge base on microplastic pollution to understand the extent of the problem. We document the quantity and types of microplastics found in our environment and monitor variations and trends. Our mission is to ensure that the public is well informed about the state of the environment and to supply high-quality data and insights that can assist further investigation into pathways and sources. Micronor is collecting samples by sort of hitchhiking on 7 already existing monitoring programs. This has enabled a rapid implementation and launch of the program. This is also a cost-efficient way to do this, but it demands additional coordination working across the various monitoring programs. We are sampling from sediments and biotas in freshwater and marine environments, and both from active air and deposition. These images give you an idea of the variety of samples we are using, from the innovative ferry box sampling to, I guess, more well-known sampling methods. In relation to the ferry box, a module for sampling microplastics was integrated in an established marine monitoring system aboard a commercial ferry, the MS Colorline Fantasy, which operates on the route between Oslo and Kiel. The testing methods we employ today are not static, but rather dynamic and evolving. Over time, these methods can and do change based on accumulated experience and advancements in technology. The primary goal of these changes is to refine and optimize the methods to ensure that they are as efficient as possible. Additionally, adapting our program to align with potential international standardization is another significant factor driving these changes. I thought I would give you a relevant and practical example from the issue of tire wear particles. Car tire particles have been shown to have a number of negative impacts on the environment. Rubber particles, like other microplastic particles, can be ingested by wildlife, which may lead to blockages in the digestive system and other negative effects. There is also a growing concern of effects on human health. Tires also contain a wide range of different chemicals, including PAH, metals such as zinc, and a range of organic compounds. Several of the tire-related compounds have recently been linked to acute toxicity for several aquatic species. Estimates suggest that tire wear particles could be the most substantial land-based source of microplastics in the Norwegian environment. In 2023, the Micro-Norway program chose to look more into the issue of car tire-related particles and urban runoff. Expanding the program, samples were collected from 2 cities, Oslo and Hamar. The results from the stormwater drain pit sample showed high levels of the tire wear particles and were consistent with tire wear analysis from sediment samples in the same area, further validating the findings. So, urban runoff was confirmed as a significant source of microplastics, highlighting the need of effective management strategies. One proposed mitigation measure is to improve the routines for emptying sediment traps in the stormwater system. This could help reduce the amount of polluted stormwater being discharged into the environment. There is also a monitoring program on beach litter. The OSPAR Commission is monitoring litter along the northeast Atlantic coastline. This initiative covers more than 70 carefully selected beaches where litter items are reported across a 100-meter span of the beach, as you see on the red line on the picture. The collected marine litter is sorted into 112 categories following the OSPAR guideline. Norway is also a part of this program, monitoring 13 beaches, and yearly reports are being submitted to OSPAR. And this takes us to the next part of this presentation, because the Norwegian OSPAR data is also shared in our database, Rent Hav. Rent Hav, which translates clean sea in English, is our national tool for gathering data from various sources on cleanup. Rent Hav also has other features. It is specially designed to support mapping, prioritizing, and coordination of cleanups. It's a user-interactive tool that can be applied for diverse purposes, such as setting up cleanup events, reporting of findings, plotting pickup points, and identifying hotspots. An additional detail about this project is that any cleanup work receiving funding must report their areas of operation and their results to the RENTAV database. It's also worth noting that this tool works inland for rivers, lakes as well, and actually any place where there is a litter issue. On this slide you see the mobile app of RENTAV, but there is also a website, and the next slide is a screenshot from one of the web pages. I thought I was going to guide you through some of the features. It's quite intuitive and not too complex. So if you all imagine yourself on an island where you're going to do a beach cleanup. You walk along the beach and you see boat wrecks and other large objects. And you can't lift them yourself, but you can use RENTAV and make your observation visible to other cleanup crews equipped with the right removal tools. They then can check off and mark these items as handled, as you see on the picture, using the before and after tick-off feature. Additionally, you can conduct a field inspection to estimate the cleanup requirements for a particular area, as you can see in the area marked in red with a binocular icon. Later in the presentation, I'll tell you also about the yellow marked area. Our app is also used in planning and coordination. It allows you to estimate and record levels of beach litter you observe. The estimation is based on the number of garbage bags you expect needed to clean up the area and is categorized into 3 levels. The RENTAV mobile application uses GPS technology to track your inspection path along the coastline. This can be done either by walking along the coast or by observing it from a boat. The estimate and tracking features are integrated, resulting in this color-coded line as displayed here. By looking at the different color zones, it becomes easy to see where there is the most waste and where we need to focus our efforts, this leading to more successful and impactful cleanups. This feature is also used in acute pollution from plastic pellets as a result of, for instance, the loss of cargo. Here you see a cleanup crew that has plotted an accumulation area, this area in yellow, as an accumulation area or hotspot, as a part of a larger operation. That's you see in the green. They have walked all this area, and then they found this beach and see that it's a lot of beach litter there. The findings from the cleanup operation, including the types and quantities of litter collected, are registered in the app. Once the beach is cleaned, it establishes a fresh baseline, so it's sort of turning into a monitoring device as well. Upon revisiting the hotspot for subsequent cleanups, we make new reports, and this puts us in a good position to see trends and pinpoint recurring items. Norway has joined forces against marine litter, and here you see the timeline of RENTAV cleanup data from 2015 until today and summarized results in this work, and summarized the result of this work. As you can see, a significant amount of waste has been collected, many kilometers of coastline have been cleaned, and a great number of people and organizations have contributed. Coming to the end, the monitoring on microplastics has had a broad approach to gather experience from many environments and sampling techniques. From our experiences, we are able to contribute to the ongoing work on international standardized monitoring of microplastics. Such standardization is essential to reach international agreements on mitigation and prevention of this challenging and widespread pollution issue. And Rent Hav is gathering and making the extensive ongoing cleanup effort visible. It allows us to truly appreciate the impact of our collective efforts against marine litter. Both the monitoring program and the digital cleanup tool are accessible online and in English, and you're very much welcome to explore them in more detail. Thank you.
Thank you very much. It was our pleasure. A nyní, dámy a pánové, bych rád poprosil.
Now, ladies and gentlemen, I would like to invite another lady to the stage. She will talk about the monitoring of pesticides in the environment and ways of their elimination. She comes from the University in Ostrava, and her name is Tereza Motuzová.
Dobrý den.
Good morning, my name is Tereza Motuzová. I've come to you from the University of Mining Technology in Ostrava and Institute. I'm going to show you a presentation not concerning the directly Norway grants, but we are kind of an analytical endpoint, and so we are open to any cooperation if actually I can show you, capture attention. I deal with monitoring pesticides in surface waters and methods of their elimination. I have introductory and part, and also research with the selected pesticides, experiment part, but then results, and also the conclusion. Monitoring of pesticides in the environment is carried out because of the growing quantities of pesticides in agriculture, and we need to increase the harvest, which would drop by 1/3, but pesticides can pass through the water environment where they are obstacle to invertebrates, organisms like eatables, because of eggs that have no shells, and also amphibious substances that try to swim, and that reduces their escape possibilities before predators. The methods are not able to capture of those substances, so there are efforts to eliminate them all the way. Another environmental problem are invasive plants that were brought to the Czech Republic initially as decorative plants, and thanks to their fast growth and seeds, but they push away the indigenous species and are able to actually change the composition of soil. And this is the reason why invasive soil seems to be suitable as material for preparation of activated carbon, thanks to which it was possible to find the use of these plants and to get rid of them at the same time. So ideas of monitoring of pesticides is first more in the surface water, in plants and sediments on banks, and also elimination of pesticides. The method of elimination and biological degradation on the basis of monitoring pesticides in surface waters. 4 pesticides were stated in all places in high concentration pesticides from insecticides. Acetamibid is the first one used for vegetables and fruits. Diphtheria is used as a repellent. Concentration up to 100%. And next one is thiacloprid, which is used for rape seeds, and the last one is piamoxan, which is used for maize, for example, corn. The monitoring of pesticides in surface waters is carried out once in a month in the places that you can see in the enclosed map, and there are actually plastic samples points, and they are then in refrigerators. Then there is a filtration and follow-up extraction. This guarantees the concentration of the samples and targeted analysis. We use SP samples from which is able to capture pesticides directly, and then as fluid or actual equipment for the detection of many of these pesticides. Monitoring pesticides in sediments, we do it 4 times a year in the same places. Like in the case of the surface water, the samples are first in room temperature dried, fully dried, and then processed, adjusted method, key 6. After centrifugation, there is a division of solid and organic phases. We use the organic phase and adjust it with XPA extraction, and we measure on the liquid chromatograph where 30 pesticides were detected. All the detected pesticides are in agreement with those found in surface waters. For all analysis, we use the Synetics XB colon, which enables the analysis of polar and non-polar substances, and also methane, and you can see actually what it does on the slide. In the next part of my work, I deal with absorption experiments for sorbents as a whole have been prepared, invasive plants used as materials, and so these on this you see actually the plants on the image. They were dried and then activated with the use of activation agents. Pyrolysis was done in microwave reactor. For in pyrolysis bank, conventional carbon was added as initiator of flame, and all the sorbents were then were reflected to neutral pH, dried, and changed to size under 0.09 millimeters. Synthetic experiments were carried out special regime, and activated carbon was added, and regular actual samples were taken, and the liquid chromatograph was used, and adsorbent experiments were carried out also in the special regime, and active carbon was left in the solution for a time which was determined on the basis of kinetic or kinetic experiments. The next method was the biological degradation, was also tested. The first one, mixture of pesticide in liquid form, 500 millimeters, to which actually 3 marimos were added, and we wanted to find out the photosynthesis. It was found out that in the pesticide solution there was actually no decline, and so the following experiments were carried out in light. So additional experiments were done for each pesticide in isolation when one marimo was added in each liquid, and the samples were taken for the period of 10 days, and the decline was measured on the liquid with the use of liquid chromatograph. Also microorganisms will be tested, which are at the stage of cultivation, We do it in Knop solution, which is aerated and is under actually flashlight in regime 16 to 8. Experiments will be carried out like in the case of those marimos, and for the period of first 10 days there will be monitoring, and then actually the marimos will left there for a month because we expect a slower degradation. You can see on the picture concentration of selected pesticides in the sampling place Kateřinský stream individual months. The results cover one whole farming season. We can see that the concentration date is much higher than in the case of other pesticides, especially in summer months when there is a high consumption of repellent substances. You can see the concentration of all pesticides increasing, especially in a period when they are applied in the field or to the fields. In the table you can see detected pesticides in sediments in the same places as the introduction. All those pesticides were found also in surface water. You can see that the 4 pesticides we have selected were in actually each of the samples. So, with regard to absorption, kinetic data were evaluated with the use of diffusion models, pseudo first, pseudo second order. You can see the cause of pseudo second order with higher reliability. We can see in the chart the absorbing the highest quantity took place during the first 80 minutes, and then the quantity actually was increasing very slowly. The absorption data were evaluated through the Landmoor isotherm, and which also provided higher reliability. We can see the older pesticides are better sorbed in sorbents prepared on the basis of activation of phosphoric acid, which is connected with higher absorption capacity and qualities with the content of oxygen and biological liquidation. With the use of marimos for 10 days, there was a decrease of concentration by almost a half. Achieved. PM-methoxam was the first, and DEEP was the worst to degrade. So in conclusion, just 4 pesticides were selected, and we still deal with them, and also 4 sorbents from invasive plants prepared. The highest sorption capacity are sorbents prepared in activation with the use of phosphoric acids, especially with the use of the special plant. The best sorbent prepared from those 2 species that I'm just there is actually Himalayan balsam, and activation with hydroxide, natrium hydroxide, a lower absorption capacity. So this work proves that invasive plants could be used for the preparation of active carbon, and the testing of biological degradation that is still in the process. We started the cultivation of other micro plants, so this is interesting for you. Please don't hesitate to contact us. We will be happy to cooperate with you. Thank you for your attention. Thank you very much. We are in time. It's very nice to see that. So the following lecturer or speaker can extend her presentation because a nice 5 minutes as a reserve. And so carbon elimination of pharmaceuticals from wastewater with the use of textile filters with carbon cake. I will take Mrs. Sylvie Křiženecká.
Thank you for having me. I am glad that I can introduce a project funded by Norway Grants. This project is called Carbon Clear. It is an operation project for cleaning the wastewater from pharmaceuticals. First, we used a biochar And further, we used textile filters. I would like to mention that we have been cooperating with Ivotech for a while, for about 4 years, and the cooperation also led to us applying for this project. As we already heard in the previous presentations, we have a problem with pharmaceuticals in surface waste and drinkable waters. And our goal was to go directly to the source of pollution and directly at the source of pollution to use our biochars developed by us and subsequently textile filters for wastewater cleaning. First, we picked a biochar that we tested to verify whether it is efficient for testing for absorption of individual pharmaceuticals. When we knew it was sufficient, we tried to prepare a pilot filter that could remove pharmaceuticals because optimizing of the filters took some time. It took us a while, and at the end we got to a final result that I would like to introduce to you now. In the first case, you have probably heard about biochars. They can be made from any material. We focused on certain functional groups that absorb various pharmaceuticals, including pesticides. As part of this project, we tested this on pesticide substances as well as pharmaceuticals. You don't probably want to work with a material like this. Biochar in this like this we don't really want to use because we want to use technology for wastewater treatment, the fourth degree of wastewater cleaning, so it's not ideal for this purpose. For that reason, we decided to use this biochar followed by a textile filter. The first attempt is this option when we used a textile filter where there was 600 milligrams of this biochar on the textile filter. Again, if you don't mind, I will pass it around. When testing this filter, we found out that the biochar was released, so we decided to come up with another variant of the textile filter. It is this prototype. This is the inner part of the filter. Here we reduce the concentration of biochar to 200 grams per square meter. So I will pass it around again. Only a few things about the characteristics. When you make a biochar from plants, for example, we use Miscanthus giganteus, for example. Here we have wood chips. You just have to fulfill pyrolysis conditions. Wood chips were digested, they were burned within 25 minutes. We have some characteristic properties here of the biochar. And again, we can notice that we have quite a high contents of functional groups. So we can have some interactions on the surface of the given material. In order to be able to try the functional properties of the biochar, we prepared classic tests. Here, we always have 2 layers. We used different layers of biochar. We did testing on pesticides, pharmaceuticals, and C10, C40. Then, when we verified the effectiveness on standard solutions, we used actual wastewater. We work both with wastewater coming from regular treatment facility as well from hospitals, because the parameters are different in case of hospitals. When we tested that biochar, we tested the first prototype of the textile filter. There were high concentrations of biochar here, and during the testing, the biochar was leaking into the solution, which is not ideal for this technology. So the first testing we did was in a laboratory. And when we look at the concentrations, we decided first we would do only 1 layer of this textile filter, and then 3 layers, so that we can compare efficiencies. As you saw in the previous presentations, concentration of pharmaceuticals differs in waters, and we wanted to prepare tests also for higher concentrations. So we tried to test first concentration on the surface of all the pharmaceuticals in concentrations 1 microgram per liter, and then concentrations 100 micrograms per liter. It was on the first textile filter. Exactly as my colleagues mentioned, we also have a problem to remove acetylsulfamexotazole on the biochar. In terms of the use of various concentrations, we can see that if we use concentration 1 microgram per liter, but you have to realize all pharmaceuticals were used, so each we were able to remove them quite successfully. However, when we increase the concentration 100 times, it is clear that the filter was not sufficient for absorption at these concentration levels. However, when we used 3 layers, we were quite successful in removing the given pharmaceuticals. These are, again, experiments. This is a pilot unit. First, we tested on small volumes, then bigger ones. Then we increased the volumes until the pilot unit. This is a comparison of 1 layer. And here, we already used the final filters when 3 variants were prepared. This is the core. This is what I have already sent to you to look at. There are 3 types of filters were prepared. This is the final variant, final one. And how did the individual filters differ? So that you have an idea of what you're looking at. We have 3 types of filters prepared for you. The first filter consists 200 grams of biochar per square meter. Those are comparable conditions. The first filter was prepared from the polyester fiber, the other types from viscose. Then when we look at this filter was also soaked in active ingredients and it had a bit different properties than the other filters. We have the three types of similar filters here. In the middle there is a core, and the core is always surrounded by another textile filters, so that the area is as large as possible of this filter. The first testing that we did in our laboratory on standard solutions are solutions of standards of individual substances. The success rate was not always perfect. However, when we look at the final results and efficiencies in individual analytes, in individual pharmaceuticals, the highest efficiency was in the filter that was called 2.1.0. So out of these three testing filters, this filter from the polyester the fiber was the best one. We made bigger prototypes from this filter. We made meters of this tested textile. We need to also know the flow rates of the wastewater that will run through these filters. So we need to know also the breakthrough curves. So we need to know how much water will actually flow there, so that it corresponds then to reality. So for each so-called breakthrough curve was tested, and this was done on actual hospital wastewater. We knew that we had only a small filter. The diameter was only 2 centimeters, and as you can see, even on such a small filter, when by the volume 100 liters of wastewater, the filter was full. What was the final result? For testing of these filters, we made this small semi-operation unit, and in this part we placed 3 filters. Here you can see the individual types of filters that were tested in laboratory conditions, and then in the semi-operation conditions you can see that after some time, we need to replace the individual filters. So here we have 3 filters, and what did it look like in the individual testing places? Here you can see from up close how the 3 filters and their positions. You cannot do everything correctly in the semi-operation. So first we tried to use 3 times 200 grams per square meter of the filter 2.1.0, and these semi-operation units were in 2 places. There were 2 of them. One of them was in Zlín, where it was tested on hospital wastewater, and the second one was in Ostrava, when there was the municipal wastewater, regular municipal wastewater. So in the first test we used 3 times 200 grams per square meter, and the second test we used also the middle filter, where the biochar content was a bit higher that was tested. These are only pilot tests. When you look at the results in Ostrava and Zlín for individual substances, we chose the substances tested in the laboratories. You can see that the efficiency of the individual filters in the operation, when the filter is directly connected to the wastewater treatment plant, that is the tertiary cleaning. Efficiency in Ostrava was about 91.6%, and in Zlín about 90.8%. it is still tested only on 3 filters. So if we wanted to have an operation where we would like to replace this unit once a month, for example, then it is sufficient to do it also according to the given flow rate in the given area. I think that the efficiency was high. The textile filter does not have the properties as the classic biochar, where the fine dust gets released from it. So I think that the textile filters definitely can be used in the future. However, what to do with the filter? You have to burn it, unfortunately. But however, the added value is that you take the waste. From the waste you produce biochar, and then the waste in the form of biochar you use somewhere else again, and then you can burn the filter. So it also provides some heat, at least. Where did we take these results? In wastewaters, we treated all the waters by SPE extraction. After cleaning these wastewaters, we did MCA analysis. Again, we are using triple quadruples to achieve better levels of detection. We would like to thank Norway Grants and also the places where the analyses are done, and also our colleagues at the wastewater treatment plants. 400 samples of wastewater were taken that were tested and analyzed, so it was a lot of work. So thank you for your attention.
Děkuji velmi pěkně a děkuji za...
Thank you very much for showing us all the samples that are still being worked on. And yes, there will be questions possible right after the next lecture. So you have a piece of paper and a pencil, beautiful tools for your noting your question and use it afterwards. So because we have now a lecture which is validation testing of advanced oxidation processes for the removal of pharmaceuticals from the effluent of wastewater treatment plant, longest title of today, and this is actually the Brno, the University of Technology, and it's Mr. Tomáš Macek. Good afternoon. So good afternoon. My name is Tomáš Macek. I'm from the University of Technology and Brno Research Center. I would like to present our project. It's the longest name to you. So in the framework of my presentations, I will introduce some summary of the project and then processes on which we focused, results of these processes, and some kind of conclusion. So what is the main target of the project? The main target was to demonstrate the use of ozonation in combination with nature-based solutions like complete cleaning stage. Micropollutants should be eliminated from wastewater. We are partners and the Technical University in Brno and accredited technical and the NINA, in the Norwegian Water Institute for Water Research. So as I say, it's an innovation project. We tested the equipment in 2 locations. The first one, from the campus of the Technical University, and there is also the wastewater from the breeding and treating of animals. They breed horses, pigs, cattle, and also poultry. And we tested only some technologies here. The second was the wastewater treatment plant Blansko, standard mechanical biological wastewater treatment plant actually with the removal of organic nitrogen and phosphorus, a size about 3,000 population equivalents. In the framework of this demonstration locality, we tested ozonization and plus the technology of advanced ozone monitoring. So some photos from some demonstration sites. This is the Veterinary University demonstration site, and then also the one in Blansko. Talking about the pharmaceuticals, we should say always what scope of pharmaceuticals we focused on. It was 141 pharmaceuticals and metabolites, and high focus or emphasis was laid on a compulsory indicative list of the State Environmental Fund, and in the framework of our 141 substances, we included here 8 substances that are included in the European legislation to come. And because we don't have so much time, I will mainly focus on the result of cleaning of the wastewater treatment plant in the town of Blansko, because testing was for a long time a more comprehensive one. For an idea, we tested ozonization as factor of cleaning treatment. Actually, we ozonized the liquids, and after ozonization, we were nature-friendly technologies that were used for some post-ozonization, like complementary treatment. So we used artificial wetlands from Grand Peace and biochar filters, and also other types of gravel filters, and we compared that with granulated activated carbon or char filters. This was the whole setup, how it looked in the wastewater treatment plant in Blansko. And the red dots are the places where we took samples, and so inflow, outflow, the wastewater treatment plant, also outflow from the ozonization units, but that was accumulated always, and from the accumulation tank it was parallel distributed to the nature close treatment technologies and on the referential carbon activated unit. So what were the questions we wanted to answer? The first one, how do current wastewater treatment plant technologies remove contaminants of emerging concern, micropollutants, and whether ozonization is effective in reducing these substances? In that framework of the project, we had a target value. We wanted to eliminate 80% of indicative substance in the indicative list in the framework of the whole wastewater treatment plant, because this was be actually a way of action that will become compulsory in the European legislation under preparation. Next question, whether the absorbents at the wavelength of 255 nanometers can be used as an effective following means of effective surrogate parameter to track the actual DCECs, and what are the some let's say positive properties or positive results of inclusion of nature-friendly technologies in post-ozonization treatment. So the main processes which we took, the first one, of course, ozonization, which we want, with the use of which we wanted to eliminate it from the pharmaceuticals. It was in water, organic substances contained, actual effect in 2 ways. The first one is oxidation, directly ozone, which is usually a slow and selective reaction, and And the second way of action is that in ozonization of water or containing organic stuff, hydroxyl radical substance, which high potential to reduce the contaminants. The other processes that we followed related to the nature-friendly technologies. Of course, some biodegradation with blood adsorption, and of course, sculptration. The third process which we wanted to explore was how to manage or control ozonization, because currently you can't make an online evaluation of how you do the removal from wastewater. Standard procedure to make samples, take them to an analytical laboratory in 2, 3, 4 days. The laboratory tells you about the concentration of substances, inflow, outflows. You calculate then whether you have done a good removal process, but you can't use it in control in real time. So this is the disadvantage of the standard procedure, and it's expensive also, and the analysis take a long time. It would be suitable to find some substitutive parameter which would at least approximately reflect the duration of your treatment process. So in the framework of our project, we focused on the parameter for relative decrease of absorbance in the 254 nanometer wavelengths, and the absorption that is used quite usually for determining the total concentration of organic substances in water. However, if you compare the quantity of organic mass and the pharmaceuticals, the quantity of pharmaceuticals is 1,000 times less. So you don't know how to determine, how to identify concentration, but on the basis of the preliminary studies, the difference, pre and after process, tells you how good you were in removing the particular pharmaceutical, and the previous studies show that should be a relatively good correlation. So this is the way the other process we wanted to follow. Now the results, which may be the most interesting part. This is removal on the indicative list of there is the wastewater treatment plant in the town of Blansko. You can see the green rectangulars indicated how the individual substances were removed in the treatment process in the plant. And if you look at the right-hand side box, it represents average removal of all those substances on the indicative list. And the average removal within that plant was between 41%, 60%. As I mentioned, our objectives was to reach 80% of removal in the process, in the wastewater treatment plant process. If you want to achieve that 80%, so out of the 60 remaining percent, we need to remove at least additional 66% in order to achieve our desired level of reduction. So if you look at the substances that are in the pending European legislation, the averages are even worse, about 3%, maybe up to 35%, depending on fluctuation. What ozonization did with this ozonization, I present the result of the substances that were in the framework of the pending European the EU directive. You can see that ozonization could enabled us to eliminate 90% and more pharmaceuticals. The more ozone, the more removal, of course. And I show you that on the y-axis there is the level of removal. On the x-axis there is the parameter of relative reduction, or there is the absorbing in the 254 nanometer wavelength. So you can say also in the basis of previous studies there is some good correlation. And if you make an average of these curves and have then the list of the indicative list, use the indicative list, you can get charts of average efficiency, effective. Two charts are here. There's the average removal of those substances depending on the flow. 3 grams, 4 grams, 5 grams of ozone are dosed per 1 cubic meter. And the second one chart shows dependence on absorption, and you can see that the differences between the dosing of ozone on the flow and on the basis of absorbance, it shows smaller dissipation, lower dissipation level. So that we can use this parameter to follow that. So, and in the second stage of our project, we tested the whole process of ozonization. We wanted to manage it just on the basis of this parameter, and we set automatic maintenance 27% of removal or of decrease. Those are the white spots or dots. You can see in each of the measurements we were above the limit that we set for ourselves. Next questions concerning ozonization is that you can create something that is even more toxic in ozonization, because some ozonization products can be more toxic, and so we monitored in our processes ecotoxicity using biotesting, illuminescence, biofisheries, because the bibliofisheries bacteria which actually illuminates in proper conditions, and if there are worse conditions, you mark some inhibition of intensity of the light which it emits. So if we look at how the results actually, now we see that this represents toxicity on outflow from it was to the plant. This is after ozonization. No shift, no difference, no statistical significance. When we compare it with the actually continuous flow of the ozonized water to the nature closed technologies, so you can see the shift is that we actually improve the water, but no statistic significance. We can't say that we are improving water, but at least we do not worsen it, which was the basic prerequisite of our project. Also, some other benefit which we have here, there is the inclusion of nature close removal technologies, so artificial wetland, for example, which is here. We had a quite high additional reduction of oxygen. Also, within the pending EU legislation, there will be more stricter limits on this. So we've been able to remove total oxygen levels, sometimes under 2 milligrams per liter even. That was okay. And we also marked a relatively high degree of removal. Those pharmaceuticals under monitoring, we were at relatively low limits, and we were able to get it under the detection limits. So low limits after ozonization, and in the artificial wetland we were practically under the level of detection. So some summary. So the present technologies for the treatment of wastewater are not able to control this broad spectrum of pharmaceuticals, micropollutants. Ozonization could remove all those pharmaceuticals under monitoring to a higher or lower degree. Because we had a quantity of pharmaceuticals when we were able to eliminate in smaller doses, like 40-50%, and advanced ozone dose method proved well in the framework of our demonstration testing, and the result, removal result, led to a more stable operation. And the inclusion of nature-friendly technologies like post-ozone additional cleaning treatment actually had some effect in ecotoxicity and elimination of nitrogen and following of some other pharmaceuticals. And I thank you for your attention. Thank you, Mr. Matek. Could you stay here on the podium? We have now a session for questions and answers. So, Mr. Krishnaskar, Motovzova, and Mr. Lund, please join us at the stage. And I believe that you can have actually the same questions for as you actually raised to the previous speakers. Yes, you have the answers now. So now, ladies and gentlemen, now if you have questions, now is the right moment. Thank you very much.
I have a question for Dr. Machko. When you actually use the ozonization effect on the water, was there any further drop there compared to the active carbon after ozonization?
Splitting.
The substances were split into other partial fragments. Did you actually focus on what kind of fragments those were, and compared to the removal by active carbon? We did not really deal with the fragments anymore. The products that can occur, there's a bunch of them, and it was not within our possibilities of analytical laboratory to go into such details. As part of this project, we decided for an approach based on what legislation requires. The legislation does not require that we focus on the removal. The legislation tells you have two categories of pharmaceuticals. From one category, you take at least two. From the other one, 4 pharmaceuticals, and try to remove at least 70%. Of course, there are other metabolites present there in certain concentrations, but we could not go into detail. In carbamazepine, we also followed 7 more metabolites, though. And then we had valsartan, 6 substances and metabolites connected with them. The overall concentration went down, obviously. Tomáš Randak, I would like to mention the ozonization. By the fact that we did ozonization, it does not remove all the problems, especially when it comes to drinkable water. In a few cases, we did ozonization without the use of the active carbon. We disinfected it with fluorine, and it was considered to be finished. However, there are other methods besides targeted screening, targeted analysis. When I look for specific substances, there is a method of untargeted screening. So it is better to look at it like this before I make any conclusions, because the untargeted screening shows me certain substances substances we cannot identify, but based on their structure, we can estimate their properties. And in this case, in the drinkable water, we saw fluorine derivatives of various substances that could theoretically have more adverse effects than the other substances we knew about. So the ozonization is not something that would solve everything. The on-target screening is a good way to go. Yes, this can happen. The same approach works in Switzerland. You ozonize the water, and after that you have post-ozonization level for management of ecotoxicity, which should degrade or remove these substances. Sometimes it is sand filtration even used when you can easily detect the adverse substances and remove them. So the final ecotoxicity of the outflow is not higher than at the beginning. So it's one of the big problems that we need to study. And of course, the toxicological tests that we used, even though it's relatively sensitive to a broad spectrum, it's not the only test available. You have other 12 or 13 biotests available to you that we could do. However, the costs are much higher, and in order to be able to find all the substances and the whole broad spectrum of these substances. Sometimes you don't ask, is this substance there? You ask, what is there? So it's again about costs related to this kind of analysis on this project. Any other questions? The colleague behind the pillar on the right. Gentlemen, my name is Robert Kvaček from the Waterways and Sewage Systems. I have a question about the textile filters with biochar. Do you think it will be it can be used also in the operation use in the future in other areas? Yes, we believe it will be. We have a patented technology for this already, and we have tested the char under the number 4073, and it has a much higher sorption properties than the commonly produced active carbon. We have already made these comparisons. Unfortunately, we cannot give away some of this information. All of this is already patented, and Mr. Kania hopes that this technology very soon will be available and it will be available on sale. Tomáš from Technical University in Liberec. I would like to ask if there's any estimate about a lifetime, because I know that the lifetime is about 1/4 when it comes to sludge. Do you think? Do you know what the lifetime will be when it's installed? Then it has to be burnt, disposed of. It will always depend on concentration when the given technology will be installed. When we have the municipal wastewater, in terms of pharmaceuticals, the concentrations may not be so high. However, we have concentrations of other substances that may be there. So we suppose that the textile filters, when when they're prepared like this already, we believe that they could be their lifetime would be about 1 month, so that the company does not have to replace them every month. So the lifetime would be about 1 month. I was not at the preparation of the textile filter at the preparatory phase, so I cannot really say how in terms of finance, what the costs are for one filter. However, I don't. Mr. Kanya believes in this and has been working with the technologies and the biochar for a long time. It is a pity he cannot be here today. He would probably tell you also from the financial point of view how it works, but he believes these filters will have also more use in the future. We don't want the classic biochar with the dust and everything. They're hard to handle, and this is much easier, and you can also burn them later. So that's all I can tell you right now. The last question, maybe? If not, so I would like to give you, each of you, a present, one bag with some promotional objects. Thank you. Ladies and gentlemen, now the lunch break is coming. So it will take 1 hour. So we will be back at 1:45, and then we will start the third block of today's conference. Thank you, and bon appetit.
action brings a reaction. They say that land is our greatest asset. For most people, farmland is the area that surrounds houses, villages, and towns, much like the sea surrounds the islands. For wild animals, agricultural fields are their home and habitat where they seek sustenance. They depend on it.
Sově pálené se věnují zhruba od roku 1984-85. To byly takové ty počátky, kdy jsem nejdříve na kole projel celý okres Olomouc a kontroloval jsem vlastně všechny sakrální objekty. Bylo zřejmé během našeho monitoringu těch sakrálních objektů, že sovy pálené z nich postupně mizí a měli jsme k dispozici historická data, měli jsme k dispozici údaje o početnosti sovy pálené v těch jednotlivých regionech a na těch jednotlivých objektech. No a protože ten stav byl neutěšený, tak logickým vyústěním byla realizace těch záchranných opatření. Jelikož jsme k sově pálené měli poměrně velký vztah, tak jsme si řekli, že musíme pro ní něco udělat. První budky jsme instalovali z vlastních zdrojů a z vlastních prostředků. No a posléze jsme začali realizovat jednotlivé projekty v jednotlivých regionech. Nacházíme se na Znojemsku u hnízdní budky pro sovu pálenou, která je v současnosti obsazená, a v budce se nachází 5 mláďat sovy pálené z druhého hnízdění. No a vlastně smyslem a cílem té naší návštěvy je zkontrolovat, jak hnízdění probíhá, to znamená podívat se, jestli tam jsou staří ptáci, podívat se na mláďata, v jaké jsou kondici. Řekněme nějakých 30 let zpět tam došlo ke změně hnízdního biotopu, to znamená i z důvodu zavírání kostelních věží sovy se přesunuly na zemědělské farmy, kde teda jim nabízíme tahleta umělá hnízda. Sovy je jako přijali. No a v těch nejlepších letech, což byl například rok 2001, tak v České republice hnízdilo nějakých 420-430 párů a jedna z nejpočetnějších populací byla právě tady na Znojemsku. Směříme délku křídla. Tady je 105 mm, to znamená, tohleto mládě je zhruba o 2 dny starší než to předchozí mládě. Do databáze u každého mláděte zapisujeme i délku toho křídla a zpětně v případě potřeby jsme schopni zjistit stáří u těch mláďat. A samozřejmě jsme později schopni zjistit i počátek hnízdění na základě data líhnutí prvního mláděte a z toho můžeme odvodit datum snesení prvního vejce. V podstatě skoro všechny páry, které letos hnízdí, tak mají druhá hnízda a ta hnízda jsou velmi početná. To je v podstatě optimální situace, kdy sovy vyvedou mláďata z prvního hnízdění a protože ta sova, dá se říct, že má nejvyšší reprodukci snad ze všech sov na světě, tak je schopná hnízdit 2x nebo i 3x v roce, ale to už jsou opravdu výjimečné případy, ty třetí hnízdění, ale stávají se. No a v prvním hnízdění ten počet mláďat bývá kolem 5-6 a pokud je dostatek potravy, sovy na to reagují hormonálně, protože vlastně samec přináší samici neustále mnohem větší počet kořistí, než jsou schopné ty sovy zkonzumovat. Samice vidí to obrovské množství potravy, takže je z toho nadšená a začíná snášet vejce, začínají se pářit a ty snůšky jsou v podstatě pravidelně anebo velmi často početnější než ty první hnízdění, protože vidí to obrovské množství potravy a takže vlastně v letošním roce máme v hnízdních budkách na druhých hnízdech, tady třeba na Znojemsku konkrétně 8-9 mláďat. To, co děláme, tak je pouze část aktivit a samozřejmě to nejzásadnější je kvalita hnízdního biotopu a prostředí. Takže my se samozřejmě můžeme snažit tu sovu pálenou vrátit do zemědělské krajiny, ale nemůžeme toho docílit bez toho, že by sova pálená měla vhodné podmínky k přežívání v zemědělské krajině. Z mého pohledu sova pálená určitým způsobem vyniká. Je to tajuplný druh, neboť žije v noci. Není možné ji běžně vidět v krajině, což jaksi zvyšuje takovou tajuplnost tohoto druhu. Žije s člověkem, dalo by se říci, pod jednou střechou a v podstatě její populace je v současnosti soustředěna do člověkem vybudovaných staveb. Ty budky instalujeme do vyšších výšek právě protože se to líbí sově pálené, jinak bychom to nedělali. Ale samozřejmě s přibývajícím věkem to může být určitý problém práce ve výškách. Na druhou stranu je to otázka zvyku a i určité rutinní práce. I na tohle to se dá zvyknout, ale je potřeba velké opatrnosti. Pokud ta sova vypadá, že je trošičku více vystresovaná nebo nervózní, tak pokud ji takhle začnu hladit, tak to vnímá pozitivně a většinou se uklidní. Tak tady vidíme vnitřní prostor hnízdní budky s vnitřní přepážkou. Ta přepážka má tam ten význam, že vlastně staří ptáci vletí vletovým otvorem, projdou kolem přepážky a za tou přepážkou se dostávají do toho hnízdního prostoru budky. A vlastně ta hnízdní přepážka jim tvoří určitý komfort při tom hnízdění, protože eliminuje příchozí světlo, které vlastně přichází z toho hnízdního otvoru. Původně sovy pálené hnízdily v přirozených biotopech, jako jsou třeba skály nebo dutiny ve stromech, ale v posledních staletích se ty populace přesunuly do lidských sídel a hnízdí pouze v nich. Ať už stavby hospodářské nebo stavby sakrální, tedy různé typy kostelů a kaplí, kde hnízdila ještě poměrně donedávna. No a člověk svojí činností sovu pálenou přímo ovlivňuje jaksi její existenci, ať už pozitivně nebo negativně. Začátky určitě jsem dělal já s bráchou, jo, to byl takový, my jsme takový tým a děláme takhle spolu pořád. Tím, že jsem z Moravy, tak jsme začali na okrese Olomouc a postupně jsme se rozšiřovali v rámci Moravy a až posléze někdy v roce 2001 jsme začali realizovat práce v Čechách. V rámci Moravy tento projekt probíhá ve 2 krajích. Jedním z nich je Jihomoravský kraj a dalším z nich je Zlínský kraj. V rámci tohoto projektu děláme management, kontrolu a údržbu 428 hnízdních lokalit, co vypálené. Druhá část projektu je realizovaná v Čechách, týká se 3 krajů. Je to kraj Ústecký, dále kraj Středočeský a Jihočeský kraj. No a na území těchto 3 krajů realizujeme management 478 hnízdních budek pro sovu pálenou. Oba projekty podpořené norskými fondy realizujeme od roku 2021, to znamená po dobu 3 let a za tuto podporu jsme moc rádi a vlastně díky ní jsme mohli v průběhu let realizovat údržbu hnízdišť sovy pálené, provádět její monitoring a aktivně se věnovat její ochraně a podpoře. Jde mi o to, aby sova pálená patřila k našim pravidelně se vyskytujícím sovám v zemědělské krajině, aby její populace byla životaschopná a aby její početnost v optimální situaci se zvýšila do období, kdy u nás patřila minimálně v určitých vhodných oblastech k relativně běžným druhům zemědělské krajiny.
Wastewater, a byproduct of our civilization. Although the water supply and sewage system is practically invisible to most of us, it is the basis of a healthy environment. It brings us drinking water and cleans everything that humans produce. It returns clean water to nature. Water is our common resource. If its quality will get worse, it can have a major impact on individuals, but also on society as a whole.
Naše společnost Pražské vodovody a kanalizace provozuje vodohospodářskou infrastrukturu hlavního města Prahy. Každý den se staráme o úpravu pitné vody, o zajištění její distribuce až k zákazníkovi, o odvádění a čištění odpadních vod. Za rok takto upravíme a vyčistíme miliony metrů krychlových vody. Věříme, že je naší odpovědností pracovat na co nejvyšší úrovni. Pro kontrolu kvality vody využíváme fyzikální, chemické i mikrobiologické ukazatele. V posledních letech máme k dispozici i moderní analytické metody, které nám umožňují analyzovat mikropolutanty. Není tomu tak, že toto znečištění by ve vodě dříve nebylo, ale můžeme to přirovnat k měření zraku. Nyní si nasazujeme silnější dioptrické brýle. Několik posledních let pracujeme na projektu, který se soustředí na odstranění mikropolutantů z vody. Jeho cílem je především minimalizace vnosu tohoto znečištění do životního prostředí. Mikropolutanty jsou organické nebo minerální kontaminanty antropogenního původu. Jejich přítomnost ve vodě a v životním prostředí vyvolává spoustu otázek a obav. Mikropolutanty mohou vstupovat do životního prostředí zemědělskou či průmyslovou činností. Jsou součástí farmaceutických přípravků, veterinárních léčiv i produktů osobní péče. Proto byly některé z nich v posledních letech limitovány ve vodním prostředí, ať již národní či nadnárodní legislativou.
Řešením problematiky mikropolutantů by mělo začít u producentů těchto látek. Musíme se soustředit na to, ze kterých zdrojů se mikropolutanty do odpadních vod dostávají. Logickou odpovědí je nemocnice.
Pro nás lékaře v nemocnicích je samozřejmě důležité to, jak se nám daří léčit naše pacienty. Ale není nám jedno jako lékařům, jako zdravotníkům, jako lidem, co se děje s těmi vodami, které tady vznikají a které odcházejí kanalizací. Jsme proto rádi, že se našly technologie, které obohatí naši čističku o systém, který vyčistí ty vody od látek, které jsou nebezpečné pro ostatní občany, to znamená od mikropolutantů, od chemických látek, od nějakých zbytků léků, anebo třeba i od nebezpečných bakterií.
Na čistírnu jsou přivedeny veškeré odpadní vody vznikající v areálu nemocnice, včetně těch infekčních. Prvním krokem je jejich mechanické přečištění. Na pásových česlích se zachytí zbytky toaletního papíru, vlhčených ubrousků i dalších větších pevných předmětů.
V rámci modernizace čistírny jsou dál zařazena bubnová rotační síta, na kterých se zachytí i drobnější znečištění. Následuje lapák písku, na kterém se odstraní částice těžší než voda prostou sedimentací.
Odtud voda přitéká do aktivační nádrže. V té se nachází směs mikroorganismů, takzvaný aktivovaný kal. Aktivovaný kal rozkládá komplexní organické a dusíkaté znečištění. Směs kalu a vody se následně přesouvá do dosazovací nádrže. V té dochází k usazení aktivovaného kalu a dalších pevných částic. Takto usazený kal je odvážen k likvidaci. Voda z dosazovací nádrže stále obsahuje léčiva. Proto pro jejich odstranění zavádíme za stávající technologii nový stupeň terciárního čištění.
Terciární stupeň čištění má za cíl odstranit zbylé léčiva a další mikropolutanty. Bude tvořeno čerpací jímkou, mikrofiltrační jednotkou, ozonizací a filtrací přes granulované aktivní uhlí. Mikrofiltrační jednotka bude odstraňovat částice o velikosti pouhých 10 mikrometrů, čímž budou odděleny zbytky aktivovaného kalu a voda bude moci pokračovat dále v procesu čištění.
Poté bude voda vedena na jednotku, která dokáže rozložit léčiva na menší látky pomocí ozonu. Po ozonizaci následuje filtrace přes aktivní granulované uhlí, v jehož granulí dochází k zachycení mikropolutantů. Díky terciálnímu čištění je voda zbavena nežádoucích léčiv a už ji zbývá jen hygienicky zabezpečit.
Hygienické zabezpečení se provádí pomocí chlornanu sodného, který zničí patogenní mikroorganismy a voda může být vypuštěna do kanalizace.
Díky modernizaci čistírny bude voda zbavena mikropolutantů s vysokou účinností. Náš projekt bude tak jedním z kroků, které pomůžou k vyšší kvalitě životního prostředí. Věříme, že odstraňování mikropolutantů z vod je budoucností zdravé a fungující společnosti. Náš projekt se stane prvním svého druhu v Česku, zaměřeným na odstranění mikropolutantů přímo u zdroje. Zásadním prvkem je pro nás podpora norských fondů, bez kterých by realizace tohoto projektu nebyla možná. Za to jim patří náš velký dík.
Climate change on our planet is a topic that brings emotion, concern, and fear among us. It can be compared to a huge building on shaky foundations that leans over and threatens to fall down on us. Part of the public is not fully aware that this is a real problem. It hopes it's just a problem waiting to happen.
Problematika oteplování nebo obecně klimatické změny sebou přinese to, co už je dnes patrně notoricky známo a akceptováno i veřejností odbornou, i veřejností laickou. A to je, že bude docházet samozřejmě ke stálému narůstání průměrných teplot, ale co je možná horší, bude docházet ke stále častějším extrémům teplotním a k větším extrémům. My očekáváme, a dosavadní data to potvrzují, že bude docházet k narůstání počtu velmi suchých let, kdy bude velmi suché léto, extrémně suché léto, větší počty tropických dnů, tropických nocí a tak dále na jedné straně, to znamená extrémní sucho, a na druhé straně ty srážky budou padat ze stále větších přívalech. Méně často, ale o to větší přívaly, což když všechno takhle vezmu a zabalím do jednoho, tyto veškeré problémy vlastně přinesou do té české krajiny ohromný problém, protože ta česká krajina už dnes není schopná zvládat současné klimatické podmínky.
Naše krajina má celou řadu problémů. Jsou to problémy, které jsou na té produkční straně a zároveň ta produkční strana se potom promítá do toho celkového hospodaření. Po té stránce krajinného rázu nebo krajiny samotné, tak velký problém je fragmentace krajiny. To znamená, krajina vlastně ztratila svoji heterogenitu a vytvořily si velké půdní bloky. Zároveň krajina vlastně tím intenzivním hospodařením tak byla změněna tak, že voda z ní odtéká rychleji. Zhruba třetina naší zemědělské půdy je silně odvodněná systematickou drenáží, která v mnoha místech urychluje ten odtok. Často, když se v létě díváme na letecké snímky na zemědělské půdě, tak vidíme sucho a zároveň tam můžeme detekovat trasy drenáží, které vlastně jsou takovými preferenčníma cestama proudění, ve kterých je zhruba akumulována ta okolní vlhkost z těch polí. Vedle toho, jakým způsobem my hospodaříme, tak používáme často ty typy hospodaření na velkých půdních blocích, které z krajiny dělají velká parkoviště, která jsou po sklizni zcela černá. To znamená, se zvětšuje výpar vody z krajiny a ten tok vody do krajiny potom vlastně odvádí tu vodu, která by se zdržela v krajině, pryč do atmosféry a potom dále atmosférickým prouděním je ta voda převáděna na další místa. V české krajině není zadržována, chybí.
My tady potřebujeme z těch ročních srážek, úhrnu ročního, maximum zadržet v té krajině a ta česká krajina to nedokáže. Takže vedle toho, že bude stále rychlejší a intenzivnější výpar díky vyšší teplotě, tak hrozí, že velká část a stále větší část srážek nám odteče z české krajiny, aniž by se využila v té krajině. A nám tady bude zůstávat stále méně a méně vody, s tím, že ta voda navíc bude přicházet v takové formě, že abychom ji jímali, tak bychom měli vytvářet další a další akumulační a retenční prostory.
Tady je nutné připravit ty dlouhodobé strategie, které vlastně dají do rovnováhy akumulace, které jsou potřebné pro velké vodohospodářské systémy a soustavy, tak aby velké aglomerace byly zásobovány a zároveň, aby tyhle velké vodohospodářské soustavy, které jsou tvořeny velkýma vodníma dílama, velkýma úpravnama, aby takováhle vodohospodářská infrastruktura měla dostatek vody, tak je nutné udělat ty plošná opatření, která jsou vlastně podstatou konceptu chytrá krajina.
To, co my budeme potřebovat, že budeme muset té krajině stále více a více pomáhat, aby ty extrémy dokázala vykrýt. Chytrá krajina je soustava pilotních projektů, to znamená projekty, které ověřují nějaké postupy, které potom můžeme uplatnit celoplošně. Jsou to projekty, kde na konci je určitá vize, krajiny, která odolá klimatickým změnám 2050+. Bude to krajina, která dobře hospodaří s vodou, dokáže hospodařit s vodou i v těch tvrdých klimatických podmínkách. Krajina, která podporuje, krajina, která nás uživí a krajina, v které se příjemně žije.
Tak na Amáli jsme v rámci konceptu Chytrá krajina umístili celý soubor opatření, z nichž to jedno z páteřních opatření je v těžišti jednoho malého povodí. Amála je pokrytá 2 párovými povodími, tak v těžišti toho povodí, které má větší podíl zemědělské půdy, tak byla postavena soustava akumulačních prvků, která je tvořena z malé vodní nádrže a je doplněna potom soustavou mokřadů, na které vlastně malá vodní nádrž navazuje. Tato soustava má za úkol jednak zvyšovat biodiverzitu v té části, která je chráněná, to znamená v nivě, která je cenná. V té nivě se vyskytuje kamenáč a tudíž vlastně tato opatření přispívají k podpoře této populace. A tím hlavním dopadem těchto akumulačních opatření je zpozdit odtok vody a získat potřebný objem vody, který je možné využít potom pro hospodaření v tom území v době sucha, pro zlepšování stavů ve vodních tocích v době sucha, protože nám nejde pouze jenom o množství vody, ale jde nám také o kvalitu a víme, že na každém zemědělsky obdělávaném poli každý zemědělec používá různé pesticidy, ať se jedná o herbicidy nebo fungicidy. A tyto pesticidy potom v rámci drenážních systémů vlastně jsou odváděny a soustředěny do říčních toků. Tak v zásadě my součástí tohohle z toho centrálního akumulačního opatření jsme umístili také mokřady, které mají tu funkci, že přispívají ke zmenšování těch koncentrací a k čištění té vody, která odtéká z té zemědělské půdy a je dotčená tím hospodařením i v rámci té chráněné krajinné oblasti při Vukolácku. Ten systém spočívá v tom, že jsme tam posílili to fungování té nivy tím, že jsme tam vytvořili umělý mokřad. Ten umělý mokřad je taková zemědělsky orientovaná kořenová čistírna, která v sobě obsahuje prvky, například biočár, které sorbují tyto pesticidy. Součástí našeho projektu je celá řada opatření. Vybraná z nich jsou již v určitém stupni demonstrace. Zejména bych zmínil cirkulární řešení pro podporu biodiverzity vodních systémů v těch místech, kde je voda odváděna. Na vybraných hlavních odvodňovacích zařízení jsme v rámci projektu instalovali přihrášky, které zpomalují odtok vody při extrémních deštích. Díky nim je potom voda zadržená a my v zásadě tento opatření ještě doplňujeme cirkulárním řešením, kdy pomocí fotovoltaické energie chceme tu vodu vracet zpět do krajiny. To znamená, že na vybrané místo, které splňuje parametrizaci tohoto systému, tak jsme schopni dovést konkrétní vodu, která tam chybí a která z toho místa odtekla. Velice zajímavým a důležitým opatřením je opatření související s podporou biodiverzity v zemědělsky obhospodařených území. Pilotním opatřením je agrolesnictví. Na vybraných částech území my podporujeme výsadbu nových stromů a zároveň, vzhledem k tomu, že Evropská unie v současné době podporuje agrolesnictví, tak my tady máme pilotní parcely, kde testujeme parametrizaci tohoto opatření. To znamená, že v té konkrétní parcele tam testujeme skladbu stromů, množství stromů.
Na tu myšlenku chytré krajiny, celé série pilotních projektů pro různé typy krajiny jsme přišli někdy před 6 lety a Amálie je prvním odstartovaným projektem. Je nejvíc skloňovaná, protože je nejdál. V tuto chvíli těch 5 let, co tam běží ten projekt, tak je na té krajině už vidět. Ten projekt Chytrý krajiny je skutečně dneska jedinečný i v rámci celé Evropy. Tak na takto velkých plochách a díky těm velkým plochám můžeme dělat systémová opatření. Máme z toho radost, můžeme se tam dnes jezdit dívat na jednotlivá dílčí opatření, ale zároveň před náma ještě minimálně 5-7 letá cesta, abychom ten projekt dotáhli do konce. Ta chytrá krajina má jednu důležitou věc oproti jiným pokusům. Ta naše území jsou prošpikována různými čidly. Takže my cokoliv uděláme, tak okamžitě na těch čidlech vidíme odezvu, vidíme reakci té krajiny, toho systému a ty obrovské množství dat, které se soustředují v centru, jsou pak analyzovány a z toho my dostáváme neuvěřitelně jako reprezentativní a sofistikované výsledky a to si myslím, že je to hlavní. To je to hlavní, co vlastně ta chytrá krajina přinese. To, že dokážeme tady adaptovat konkrétně jednu krajinu je fajn, ale to, že máme tam čidla od začátku, než jsme to začali adaptovat a budou tam až do konce a budeme to sledovat ještě samozřejmě po ukončení adaptace, jak se ta krajina chovala před, během a po. To je to nejcennější. To je to nejcennější a tohle my musíme vyhodnocovat, protože z toho pak vypadnou ty nejúčinnější a nejlevnější řešení. Na adresu norských fondů já bych hrozně rád těmto fondům poděkoval. Poděkoval jim za to, že tomu našemu projektu uvěřili a že skutečně vlastně slyšíme i tu odezvu, že věří něčemu, co dává smysl do budoucna, že to není jenom, řekněme, obyčejný ozeleňování krajiny, ale je to něco sofistikovaného a zároveň to té krajině neubližuje, ale velmi jí to pomáhá.
It is said that we should carry in our memory the lives of those who are no longer with us. Once we forget, there is no way back. There are people among us who are trying to return to our nature what we have almost forgotten.
Populace lososa obecného v našich řekách úplně vymřela. Pokouším se obnovit tuto populaci nejen proto, aby děti neznali lososa pouze z chladících pultů, ale proto, aby viděli tuto rybu i v divoké přírodě.
My sa dívame na jednak historický výskyt tých jednotlivých druhů rýb, ale skoumáme v podstate, kromě toho historického, i ten súčasný stav. A pri tom súčasnom stave sa díváme na tzv. Habitatové podmínky. Když vyberáme vhodné lokality, kde inkubaci dělat, zabýváme se různými charakteristikami, které ovlivňuje proudění vody. Musíme si tam jednak zmerať, jak vypadá to koryto toho vodného toku, veľmi detailne. Na to používame zase nástroje geodetického merania. No ale kromě toho taky hydrometrujeme, to znamená, že priamo v teréne na tých konkrétnych lokalitách, kde tie inkubaci dochází, sledujeme v průběhu roka povodne. Zabýváme sa suchým obdobím a pri týchto obdobiach riešime konkrétne rýchlosti proudení. Pretože tá rýchlosť môže výrazným spôsobom ovlivniť život toho lososa, respektíve všetkých lososovitých rýb, ktorými sa zabýváme. Ale pomocou tých několika meraní, ktoré v průběhu toho projektu získame, sme schopní získať nejakú informáciu, jak ten prútok vypadá presne v tom míste a to nám extrémnym spôsobom pomáha spresniť a skvalitniť tie modely. V tomhletom projektu navazujeme našu predchádzajúcu prácu, takže aj tých výber tokov, kde tá inkubace dělá, kde to hodnocení tej vhodnosti děláme, tak navazuje na toky, ako je Kamenice, ako je Malé Labe, ako je tok Lomná. No a k tomu sme pridali 7 dalších, čiže dokopy máme 10 lokalít v rámci celej Českej republiky.
Zásadní vlastně lokalitou pro inkubaci jiker lososa je jediný potenciální vlastně tok a tím je řeka Kamenice v Národním parku České Švýcarsko. Je přístupná ze Severního moře, vlastně Labem, kdy Labe je až vlastně po Českou republiku, dá se říct, průchozí. Jedinou migrační bariérou přes Německo je plavební stupeň v Gesachtu, který je opatřen vlastně 2 rybími přechody. Čili Kamenice je vlastně takovým prvním přítokem na našem území, který má smysl pro obnovu aktuálně lososa obecného. Klíčovou roli tato schránka hraje při inkubaci jiker lososa, protože, jak potvrdili studie, losos nebo lososí jikra se musí vyvíjet již v mateřském toku, protože už v době tvorby toho zárodku nebo vývoje zárodku v jikře si losos zabudovává vazbu na to mateřské prostředí, to znamená, že si zapamatovává chuť té vody, když to takhle zjednoduším, a následně mu ta vlastnost homing napomáhá vracet se zpět do míst, kde se losos narodil. Zvyká si tak na tu potravu, která se v té vodě přirozeně vyskytuje, protože schránka je průtočná a dá se říct, že mikroorganismy, které se v té řece vyskytují a které slouží jako potrava nebo za potravu tomu plůdku, tak vlastně pronikají těma sítama dovnitř. Tyhle schránky, které jsme pojmenovali lososa, vznikly za účelem inkubace lososích jíker v Národním parku České Švýcarsko a aktuálně tak se v nich inkubuje i lipan podhorní, což je také lososovitá ryba a vlastně zkoušíme tuto schránku i na dalších říčních rybách, jako je třeba pstruh, ostroredka, parma a nebo podoustev.
Vďaka podpore norských fondov sme byli schopní osloviť ďalšie inštitúcie nebo organizácie ryby, spolky konkrétnych osoby rybárov a rozšíriť tak metodiku, ktorú vlastne používame do ďalších miest v rámci celej Českej republiky a medzi ďalšie lidé, ktorým nie je hostejný život nejen lososu, ale aj ďalších rybých populácií. A pevne dúfame, že to, čo sa nám podarilo inovovať, zlepšiť i vďaka norským fondom, môžeme ďalej rozširovať nejen v Čechách, ale tie naše znalosti posunúť a v spolupráci s partnermi v iných krajín sa snažiť o tú inkubácii rôznych druhov rýb v rámci Strednej Európy i napríklad v rámci projektu Interreg.
Naši milí hosté, za 5 minut budeme začínat. Our dear guest, we are going to continue in about 5 minutes. So, 5, yes, right.
When someone starts a sentence with the words human hand in the sense of the environment, it usually does not end well. Somewhere, as humans, we changed nature in such a way that it almost became a desert for specific species. They lack food and a place to live. Dozens of species of birds, plants, and insects began to disappear from our landscape. Unfortunately, some of them are almost on the verge of extinction. Fortunately, new islands of hope slowly began to appear on our map. Sanctuaries that will help all living things survive and return in the future.
My jsme nějaký čas hledali místo, kde bychom mohli realizovat naši myšlenku budování ptačího parku. A vybrali jsme si právě toto místo severně od Jarohniveckého rybníka u obce Dubňany z několika důvodů. Jeden z důvodů byl ten, nebo hlavní důvod byl ten, že je tady pestrá mozaika různých prostředí biotopů, jsou tady místa úplně mokrá, jsou tady místa suchá a je tady jako pestrá škála těch přechodů mezi rybníkem, mokřadem, vlhkou loukou, suchou loukou a nad tím ční, dá se říct, až takové jako suché písčité hrůdy. Takže toto je pestrá škála biotopů, která skýtá pestré podmínky a tím pádem je tady obrovský potenciál na to, aby tady byla pestrá příroda. Předtím, než jsme cokoliv tady začali dělat, tak tady proběhl rozsáhlý monitoring a mapování, co vlastně tady máme. V rámci toho území jsme našli takové, dá se říct, malé ostrůvky s původními druhy a s hodnotnou biodiverzitou, s potenciálem kolonizovat to prostředí v případě, že mu ty podmínky jako naskytneme. Ten druhý důvod, proč jsme si vybrali toto území, byl ten, že toto území bylo dlouhou dobu opuštěné. A nás právě na tom lákala ta výzva vlastně přeměna nebo rekonstrukce těch biotopů. My jsme přišli do prostředí, které bylo totálně zarostlé zlatobílem, který tady rostl v obrovských plochách. A právě přetváření tohoto prostředí s potenciálem na zajímavé původní biotopy. Mokřady jsou velmi pestrým biotopem v našich podmínkách, kde je voda, tam je i život. Co je důležité, je, aby toto prostředí bylo vlastně nějakým způsobem manažováno, nějakým způsobem udržováno.
Nacházíme se na pastvinách, konkrétně u jedné tůně, která byla vyhloubena. Těch tůní je tady několik a plní několik funkcí. Primárně ty tůně jsou zdrojem vody pro samotný dobytek. Ale hlavním důvod je, že z této vody, z těchto mělkých tůní profituje celá řada dalších organismů. Třeba obojživelníci, anebo hmyz vázaný
Naši milí out dear guests, I hope you enjoyed the break. Doufám, že jste si užili přestávku. Už jste tam. Krásné. Že vám chutnalo, co jsme...
I hope you enjoyed the break, that you liked the refreshments, you are refreshed and you are full of new information. You have many questions written down that you can pose at the end of this third session. Maybe you have also some questions about the presentations from yesterday. It is already 1:45, so it's time to start the third block of this two-day conference. And the first speaker on this block is Robert Kvaček, decentralized my removal of micropollutants from infectious hospital water. Robert Kvaček, Prague Water Supply and Sewerage, ANC. All of us are full now after lunch, but we are ready for your presentation. Good afternoon. My name is Robert Kvaček. I'm from the Prague Water Supply and Sewerage. I will follow up on the topics the speakers talked about. We talked about monitoring pharmaceuticals in the landscape, what the laboratory options are in the semi-operations, and I will introduce to you our project focusing on the operational application in the Czech Republic, pollution of micropollutants in hospital wastewaters. The project is called the Decentralized Removal of Micropollutants from Infections Hospital Wastewaters.
So what will be the content of my presentation? We will introduce shortly some basic parameters of the project, and I actually tell you something about our expectations and set targets, and then we will look at the implementation. I will introduce you the wastewater treatment plant of the Prague Tomayer Hospital, technology equipment, what interventions we have made, and what results based on laboratory analysis we have achieved, and what is in store for us in this project, because it's been actually going on since 2022 so far, but of course the work is not ended yet. So our project as such was approved in a two-round call, Trondheim. Actually, we used very similar conditions to those mentioned by the previous speaker from the Czech Technology University of Brno, because we same indicative list of pharmaceuticals. We had cooperation with the faculty hospital, Tomayer Hospital, and also it was based on a public order of Mega AS company. We were we have been supported by the Norway Grants, a total amount of 23 million Czech crown, most demanding, most costly project in the framework of that call. And so what we are interested in, the call actually has been focused on eliminating pharmaceuticals from various types of water. We have chosen the hospital wastewater for some reasons, because we think that it's actually most concentrated source of contaminant which we can find in routine practice, normal practice, and we wanted to show, in spite of the fact that the Czech laws are the topic of treatment of hospital treatment or wastewater treatment, and hospital subjects are not actually included, and it will apply now to us now with the amendment of the directive on the treatment or the 91 to EES. And we still, it will be of a large population, where we still have tens of years, of decades before we can get those actual clean technologies, and God knows when the hospitals will come to the front. When part of the hospitals could use that, technically it's available, but accessible, the problem is somewhere else. It was mentioned before, if a hospital has a wastewater treatment, then it's in bad situation often. With regard to the fact that the hospital wastewater treatment is supposed to treat people, and so there are not many funds available for that. So this endeavors of modernization actually or go beyond the regulatory framework, it's usually not there. So we wanted to do the first quarterly hospital in or cleaning of hospital or treatment of hospital in Czechia. We had to comply with the requirements. 90%, such as 90% of average concentration of pharmaceuticals should be covered, and it's been also our target has been to set afloat the discussion among economic experts that there's such water, that it exists, and that we will also deal with the removal of pollutant from more diluted municipal waste. So we can target on these important sources. Very implementation of the project as such consists of three parts. The first two of smaller nature, actually disinfection of outflow. If there is rain actually in the wastewater treatment, there is a higher influx, and then the water automatically spills over the sewage system, but it's, because it's infectious water, it should be disinfected according to Czech technical standards. So we had to deal with it, and we added also mechanical pre-treatment. And I will talk, I will spend most of my presentation on the quaternary line. The wastewater treatment plant was built in the 1960s for 1,500 equivalent citizens. This table shows the average flow rate, and it's about 200 cubic meters per day. And our technology has been actually dimensioned so it can do with this amount up to 300 degrees. So of course it's a hospital, not a long activity of employees, long time no influx of water. Without additional accumulation, you can't treat the whole amount of the water. We get normally at to 80-90%, which actually is are subject not only to the regular treatment but also the quaternary. Our plant is the quite usual treatment part. On the left-hand side, you can see inflow. On the right-hand side, there's the spillover. There is the disinfection with the NaClO. And on the right-hand hand, this actual sand trap is automatic. Then it goes to the sand trap and dual activation tanks that were intensified some years ago. And the right one is standard as aerated aeration tank, and the left one is for activation of sludge. That's the biological stage, and separation is done in quite normal circular basin, and so this wastewater treatment plant is supposed to do with the carbon activated and to do aeration of ammoniacal nitrogen, what it must do so that it can actually do the disinfection of those waters. So we have the dosing here of the NaClO. And so this water actually flows to the sewage system, and it is retreated also in the central wastewater treatment plant. It may be curious, but actually it is the usual practice. Just to give you a good picture, the wastewater treatment plant is is next to the Kunratice stream, which is middle size brook. And so, of course, it's important for the whole ecosystem. So now, our technical solution within the project and the results. First, the hygienization or sanitation. The first, I'm not going to talk about it. Second part is the addition of the mechanical pre-treatment, and we included between course rec and the sand trap rotation screen was added, and actually to reduce the number of not diluted substances which would actually be a problem in the regular networks. On the left hand side, the draft, the proposed design, and on the right hand side is the genuine one. And the quaternary line now, on the basis of literature, operational experience, was mentioned. The only country in the world that has transferred to semi-operational practice is Switzerland, but the EU legislation does not provide for that. And Switzerland is also a quite wealthy country which can afford to have such equipment. So many wastewater treatment plants that have such technology, and in combination with absorption with the actual granulated activity carbon. We decided for the activation. We had microfiltration before that, and we decided in favor of ozonation because we wanted to have the cleaner in outflow, quite clean in outflow. The design was approximately like this. There is the proposed design. We used the technology. We took the treated water from the previous stage for actually accumulation tanks, and there was a pump which puts the water to microfiltration stage, the first one, and then there's a repumping station or pumping station. It goes to 5 cubic big tank, then ozone diluted in certain stream of water, and there is reaction here when there is fusion, and some substances, some are just deactivated, and some leads to the creation of some semi-products which should be then eliminated, all of them in sorption process in the second filter. And the water goes to the big tank, and it is that big because if the filter is granulated active carbon, actually you have to deal with it, and the whole tank is used. And then there is a micro treatment which I introduced to a minute ago, and in the future the treated water can be applied also otherwise I will get to that later. So this was the model. What is the reality? Reality microfiltration. We spoke about 500 micrometers. Now it is 10 micrometers, so 50 times finer screen, and of course it is clogged very often. You have to flush it, pre-treated water, and there is also some measurement parts which are used for considering the efficiency of the cleaning process. Then you have a snapshot of aerial view. Installed equipment for actually taking away the residual gas which gets above the surface, and in the follow-up it has to be deactivated. destroyed, so that the ozone cannot get in the environment where it can be harmful. It is actually decomposed and it's taken out of the building. Ozone as such is generated directly in the wastewater treatment plant. It's an equipment that consists from a compressor, and there's the coronary development and some kind of storage of the produced gas, which is then dosed to water. And of course, ozone is quite toxic substance. So you have to think about the health of the employees. So there are sensors also, and so we monitor and keep the ozone concentration under 0.3 micrograms per filter. And the filters are designed in such a way so that only one actually can do the whole amount of influx if the other one is not operational. So this is the wastewater treatment plant. What flows out of that? First, I will briefly introduce you the basic physical chemical characteristics, and I will get to pollutants. I will talk about three places. This is inflow inactivation plant. It is for us in the wastewater treatment plant. There is from the previous tank, and there is also a flow into the new equipment, and the last one is there is the outflow from the quaternary technology. Looking at the efficiency of the indicators of the chemical consumption of the oxygen and deactivated, and the total amount of the chemical substance used. Here, the first line achieved some values which can be within the limits provided for by the government decree in valid wording, which can be sent into the recipient, and between the outflow output and there was 80% or 100% elimination of those properties. So the technology can do with diluted substances. It can reduce the concentration of chemicals, including also the micro pollutants. And of course, we had a maximum possible scope of the 150 substances, chemical substances, but we actually evaluated only those included in the indicative list. There were about 33. We actually identified 30. Then actual inflow in the wastewater treatment plant from 15 campaign, 520 grams, and so. Like if we talk about the monitoring, I think that actually it corresponds. The individual substances are corroboration. Of course, these are chemical substances. They biological process for the treatment, and some of the substances are biodegradable, so it can do them. 520 milligrams per square meter, 46 micrograms per liter. So there is a 90% decrease here, but this is still a value which is quite high for us. So we can put the water in some environment. Our requirement was out of the 43,000 to remove actually 90%. Actually, the result of the campaign is that the average concentration 100 was more than 92% efficiency, and the technology is still quite new, and it will be aging, of course, and the results can get worse over some times. But even this has been quite a nice surprise to us that has actually exceeded our expectations with regard to the individual substances. On the inlet in the quarter equipment, we detected at least 28 of 30 present. So there was a whole scale of those substances coming from the hospital. The contrast substances were actually used here at the highest possible concentrations. And on the outflow, we got into a situation where we detected at least one of 15 samples, and visited at least 5 of those. And those were the following pharmaceuticals. All of them had been mentioned. Here I will just speak about metformin, because these are substances were detected just once, maximum 2 times. And these are some averages of removal. On the right-hand side column, we didn't calculate those provided values. in spite of the fact, even with the most problem creating pharmaceutical metformin, we get to 88% infection rate. It will be reduced. Because the treatment, wet treatment we can do with that only very poorly, but all the other indicators are liquidated actually quite well. Looking back of what the project has brought us, in spite of the troubles with the filing of public quote, the state hospital had to file, so we were able to install the first quaternary treatment, wastewater treatment plant to install, so it is working. It will need to be optimized, but we want to send a signal to the water supply company, water management company, that it can be done. Of course, it can bring some complications in the form of higher operation cost for the hospital. It can be, but it can be also an interesting investment, and what is really thing which we want to cope with in future. And then when we get the sufficient number of data, and then we can actually let the water that has been treated to the neighboring stream, because it usually lacks water. And if there are more such projects, and especially projects in the case of the flows, like mentioned in the first lecture, that it was a majority share coming from the hospital treatment, so we could improve the functioning of that actually facility in the ecosystem. I think that this is kind of a pioneering project, and I hope that the next operators and hospitals will follow up to what we have done already. In conclusion, so you to see what you could see the individual stages, 1, 2, 3, and then finally the almost crystal clean water. First of all, I want to thank the Norway Grants and the State Environmental Fund for support and choosing us and actually shooting one of the documentaries for us, and I would like to thank you very much for your attention. I showed you 5 minutes left for you, so we're able to do it quite nicely, quite quickly. Let me invite the second speaker of the third part, and this use of advanced oxidation process for efficient removal gabapentin and ibuprofen from the wastewater. It's not too crack for the interpreters, and Mr. Martin Vashinka.
Good afternoon to all of you. I hope you had a nice lunch. Welcome to my presentation dealing with the use of advanced oxidization process to remove gabapentin and ibuprofen from wastewaters. A lot has already been said concerning the granulated active carbon or biochar, and also about the oxidation processes. So it will be just in addition to what you have already learned today, and an introduction of a new possibility, new combination, how to get rid of micropollutants from wastewaters. The realization of this research dealing with the analysis of gabapentin and ibuprofen was based on oxidation processes in Moravský Beroun project, where we agreed with the town of Moravský Beroun to implement this research in their facility and to test our technology as a pilot. The significance of this project is that the recipient is in the protected area of Ondrášovka, And the aim of the project was the installation of a pilot semi-operation of a tertiary level of wastewater cleaning. The main substances we focused on were gabapentin and ibuprofen. The goal of the project was to remove gabapentin and ibuprofen from Moravský Baron wastewaters. The main goal was to achieve effectiveness over 90% in these two substances. Using mobile technologies in the more advanced oxidation processes in tertiary cleaning of wastewaters. When we look at these charts, we can see that ibuprofen on the left, you can see substances detected in the environment. You can see that the most represented substances are the anti-inflammatory substances. Ibuprofen is one of them. Ibuprofen is synthesized every year in about 30,000 tons every year. So there is a big potential that this substance will also be in wastewaters. The other monitored substance is gabapentin. It's an anti-epileptic. And the epileptics represent about 8% in the environment. This is from publication Hank et al. From 2018. We can show this to you also in surface waters in Europe. We can see if we don't include fungicide compounds and antibiotics, you can see that they represent a big part again. Also those including gabapentin. When we divide the substances very quickly, ibuprofen, as I have already mentioned, is one of the non-steroid inflammatory substances. It is it has antipyretic effect, analgesic effect. As you know, it's against fever, and the dose, the effective dose, starts at 200 milligrams. That means not in grams, but in milligrams. The rest of the tablet is usually magnesit, for example, in case of paracetamol. It is in the form of syrups, tablets, and drugs for local use. Among them is ibuprofen, Ibalgate, Nurofen, and then another one is anti-epileptic is gabapentin. It is to treat epilepsy and neuropathic pain. It has already peripheral neuropathic pain. The common daily dose for an adult is 900 to 3,600 milligrams. It exists in the form of tablets or capsules among the drugs gabapentin, teva, gabapentin, aurobindo, and Neurontin. As I have said before, ibuprofen is yearly synthesized in large amounts. It is not so hard to remove them from wastewaters. However, the concentrations are very high, so the residual concentrations are still very high, even though the efficiency is very high. Another reason gabapentin was chosen in Moravský Baron, there is a hospital that focuses on neurology, and gabapentin was a good candidate because it was in high concentrations there, and at the same time, it is quite hard to remove from wastewaters compared to ibuprofen. And here I prepared for you As we said before, the drugs can work as a cocktail in a synergic way, and sometimes it is necessary to separate the effect of toxicity, and we need to monitor the substances separately. Here are some few examples of toxicity that has been proven in case of ibuprofen. It is, for example, the reduction of viability of useful bacteria. For example, Bacillus megaterium and algae, chlorella. Also, there are adverse effects on reproduction of fish. For example, Oryzias latipes, Japanese rice fish. It may also have effect on disorders of brain and kidneys in zebrafish, or deformation of liver and gills in Clarias garipineus. And of course, it also has adverse and chronic effects on human health. In gabapentin, we don't know much about it yet, because the substance is not so well researched in terms of its toxicity on a broad spectrum of organisms. And that's why we are still waiting for this research. And the biggest environmental problem now are the products of the transformation. That means the metabolic products. The products of the transformation. It may be the advanced oxidation processes of or products of the biological transformation. They may be more toxic. Gabapentin lactam, for example, is more toxic than the gabapentin itself for embryos of the zebrafish. So it is necessary to study the products that and the residues of the transformation. And simply and quickly, the advanced oxidation processes are environmentally friendly methods. However, the dilemma is this really environment-friendly method if some products or substances are produced, maybe even more toxic at the end. It is clear that these substances are produced. Of course, this has not been tested on a number of organisms. Each organism will respond differently, so this is still an open topic for now. This advanced oxidation process method is based on the hydroxyl radical. The oxygen radical then reacts with water, and the hydroxyl radical is the result. It is highly reactive, and it can oxidize the drugs. But there is still a possibility that some negative substances will result from this in terms of toxicity. Now, this is the box model of our technology that we tested in Moravský Beroun. The technology was connected with a was done in was tested in Moravský Beroun. We cleaned the wastewaters. We used a disc filter to catch the impurities. Then, after catching these bigger impurities, the advanced oxidation process unit followed, which was divided into ozone generator and 4 low-pressure UV lamps that were used in the second part of the unit. And then, to increase the effectiveness, the following UV unit was selected for secondary UV radiation, followed by accumulation tank, and then to increase the efficiency of this technology, it was possible to use the recirculation pipe and do the recirculation phase. For that reason, we tested 4 recirculation phases. However, it is not limited in number, and we also tested various flow rates. I will specify it later. After the recirculation, a tank with granulated active carbon was prepared that was supposed to catch what we had not been able to remove in the previous technological procedure. And this was followed by the pressure sleeve filter, which was here in case the particles of the granulated carbon were released. It was already mentioned here before that these particles may actually be released, and for this reason, this pressure sleeve filter was here, and it was followed by the outflow of the cleaned water from these oxidation processes. I will mention also that the height was 1 meter at the end. Testing of technology. We tested the technology in 5 rounds. We tested flow rate 1.5 to 2.3, 2.5, 3, 4, 5 cubic meters per hour, and we used 0 to 4th recycle. In parallel with the testing, we also took samples of wastewater. There are 5 rounds of testing and 5 rounds of taking samples. So we followed the concentrations of ibuprofen and gabapentin and removal of these primary drugs. We also did supporting analysis focused on changes of basic chemism of waters. I also prepared some data here concerning the results of some specific tests. You can see that in case of ibuprofen, the efficiency of oxidation processes was much higher than in gabapentin. It is given by the variability of the pharmaceutical, the chemical structure of the pharmaceutical, and each will respond differently to the reaction with the hydroxyl hydroxyl radical. It is also possible to observe that in the 3rd recycle, we got over 99% in terms of efficiency of removal in ibuprofen and about 95 in gabapentin. So the efficiency was over 90% already at this flow rate. This is the drop in concentration. And so here we tested also the effect of the granulated active carbon. Technologies were introduced here today that focused on the granulated active coal. Makes sense. It does work. It works very well. However, the significance of the process is that when all the absorption spaces will be filled by the coal, it will have to be reactivated. It will have to be replaced somehow. So there is this pre-step here of the advanced oxidation processes. So some substances already get degraded, and this may actually extend the efficiency. So if we take the everyday operation, it can actually prolong the lifetime of it. Here we can see that every time, no matter what the recycle, there is a in recirculation of the wastewater in both drugs. We can see that the efficiency of removal was over 99% after the filter with the granulated active coal. Here we tested also what would happen if we did not use the ozone. That's this second part. We would actually leave out the hydroxyl radical generation to see the drop. if we compare the zeroth and second recycle, we can see that in case of ibuprofen, the drop was 58%, in gabapentin 50% here, in ibuprofen 46%, in gabapentin 50%. That means that the phase or this step is important. Interstep is important, and the granulated active coal at the end is a very good combination. Here we can see the Durov diagram. This is also an interesting thing. The mineral water Ondrashovka consists a lot of calcium. And based on this information, we knew that there will be also these ions represented. Also, pH was between 7 and 8, where we have HCO3 minus. When we compare to 2.3, the flow rates here per hour, we can see that the heterogeneity was especially wastewater is always heterogeneous in time. So that means also concentration of the pharmaceutical is heterogeneous in time. So the mineralization is always different too. So, but however, if we should assess the influence on the chemism, on the dominant ion composition, the technological procedure does not affect it, which is an interesting result. The only influence was increase of a small increase of pH after the granulated active coal was used. The one that we used contained over 10% of ash. So the coal that we used was not chemically activated. So that means that the generation probably was actually produced by steam. That means that the carbonates could be generated from the ashes in the coal. That's possible. When we look at the column diagrams, we see that what dominated was the natrium, and HCO3 and NH4 and HCO3. When we analyzed this, we realized that ammonia was dominating. The growth in ammonia concentration may be a result of incomplete nitrification at the outflow from the waste water treatment plant into our inlet, or the degradation of the organic mass, because each organic mass contains AMK, which then changes into ammonia. At the end, I would like to say that the use of this technology was successful in Moravský Beroun. So we were able to reach the success rate over 90% when it comes to removal of the pharmaceuticals. As I have mentioned, the efficiency of the technology will probably vary by type of micropollutants or pharmaceuticals. So that's why it was variable in case of these pharmaceuticals. In lower flow rates, there is a longer time of contact, and that's why also higher efficiency of removal. So then hypothetically the efficiency should be higher in this case. Use of ozone, of course, is necessary in order to get to the highly reactive hydrogen radical. Technology did not have a significant influence on distribution of dominant ions in the water, and the technology is already protected by patent, by a utility model, is mobile, and it is stored in a transportation container, and it is a very good choice to do it this way. Thank you for your attention.
Děkuji moc krát za
Thank you very much for your presentations, and we have now last presentation of the two-day conference of ours. And the gentleman who will be last here is a man who we have the lecture of reduction of pollution of surface water, pharmaceutical substances in biological treated wastewater. You have the longest title of your presentation is the Technical University of Liberec. Mr. Tomáš Lederer has the floor. Thank you very much for giving me the floor. Good afternoon, ladies and gentlemen. I'll introduce myself. I work in the Technical University of the town Liberec, in actually the Department of Wastewater Technology Treatment, and I had some previous background also in a similar field. Now, regarding the motivation that have led us to removal of micropollutants, they're mentioned here, in spite of the fact that the subject of micropollutants is something that we have dealt with, especially in industrial water, pharmaceutical, paper making, in the pulp making, pulp and paper industry or chemical industry. So one of those motivation factors is so that we are actually contacted by manufacturers of those special filters. So we actually deal with the removal of the residual substances of those latex, and we also have dealt with in our time with the solutions of extreme requirements for the reduction of the total organic load of wastewater treatment plant. Last but not least, what I actually emphasized here in red letters, there was actually amended directive on the treatment of municipal wastewater last April, approved, and we have the support of, enjoyed the support of the Norway grants. I will skip many of these things because many of them have been mentioned already. So there is especially the list of pharmaceuticals. We have based on 3 wastewater treatment plants, various types. One of them was the big one in Liberec, town Liberec. This is a regional town at 10,000 equivalent. Next one, distribution center Amazon, near the airport here in Prague, and also the wastewater treatment plant in the village of Dobrovize near Prague, same region. Concentration of pharmaceuticals in inflowing, outflowing water are quite changeable depending on the type of substance. They are significantly reduced. Sometimes it's more than 90%. Sometimes it's less than 50%, but what is substantial on the basis of research data, it's been interesting data about the river basins, that the main thrust of the pharmaceuticals is in wastewater, not only outflow from the wastewater treatment plant, but also the bypasses of actual wastewater treatment plants at times of torrential rain. And this is also a subject of the directive, and there are some percentages, as I mentioned, which almost can't be imagined actually. Because there may be up to 50% inflow. It's a huge challenge, especially regarding the big towns where you can't do much about the, in view of those sewerage systems existing there. So with regard to the implementation of elimination in connection with the motivations, I will skip that. And I will do now go to the specific project. So Kodak company is the actually main subject dealing with the wastewaters, and they do also automatic modeling of those processes. And the significance is what I get to in the end is the subject adoption of the new directive. After that, after the adoption, how to do this issue, to resolve this issue in our industry. We actually dealt with some advanced oxidation processes in our laboratories, and it shows 2 pilot tests in the wastewater treatment plant in Liberec in Amazon one. And the composition is before the primary filter, which was filled with a catalyst, a magnetic catalyst. Before that, you put the peroxidal and filter, and so pre-treated water went to the biological column with carriers, and what is not an absorption endpoint. You will see that in the next slide, which was content with granulated active carbon. As far as the chemical laboratory, what we dealt with very much, and it's is the pre-treatment stage with regards to the treatment process of municipal wastewater. Everything can be is viable, actually technical. Everything is just subject to costs. There can be advanced processes used with the end phase absorption pace. You can deal with that. But on the cost side, especially, is the life cycle of active carbon, whether it will be regenerated or will be replaced. And so what is determining the life cycle of the activity carbon is the total concentration in the wastewater treatment plant. We can get that in 2 ways, basically, by building supply water works technology for treatment, and the works that the biological resistance is the different in comparison with the surface water. For example, coagulation by aluminium, not very successful. We have been most successful with coagulation, ferrous coagulation, of course, but there was a drop in pH values. But for the whole organic, we can go to some 50%, which plays, of course, an enormous role in the absorption process. So, and then we also, in our laboratory, we dealt with the 3 possible ways to do it. Advanced oxidation processes with the pilot testing, used the catalyst with magnetite as the source of 2^3 iron, and we also tested oxidation of UV filters, the peroxide and UV factors, and also yes, and in our laboratory we did that with absorption testing for a long time, so to get an idea about the life cycle of the activated carbon after we actually bring the wastewater from the pilot stage to it. So I'm skipping. I have selected some pharmaceuticals in those treated in those laboratories. Those that could be done best are mentioned here. But also you can see independence in concentration of the peroxide, which would from 0 gram to 2 grams. You can see the efficiency of the removal, and I must be doing incorrectly something. So we then he went to the pilot projects, the equipment composition. This is what I mentioned already. I don't know what this is doing. Maybe holding it for too long. I apologize. That brings me to summary. Okay, I can do the summary and then go back to the details. So, go back some slides. No, out, and here we are. Maybe this one's just to make conclusions, that's all. Nevertheless, when I'm jumping to the conclusions, I will tell you something which is most important about the conclusions. Most important is how to reduce the burden of the final sorption stage, but also the oxidation stage, because the total sum of organic substances, of course, it's a burden for the oxidation agents, peroxide, or perhaps in ozones in our practice. So the reduction of the outflow concentrations in the wastewater treatment plant, well-functioning wastewater treatment plant with between 20 to 40 milligrams. Acronym is KSK, and we have experience from the operation of the Amazon wastewater treatment plant, which has big ranges depending on the commercial or trade peaks, and then we do twice as much as the usual routine municipal actual wastewater treatment plant. So when we actually project it to 2 days, then we get really to half values. KSK, and of course carbon, and it is connected with the burden on the whole process. This is one of the future ways which are on the table, and which especially my colleague Novak deals with when modeling the processes. So in a real situation, in real life, in a future real life, the Liberec wastewater treatment plant, which is 6-lined with the capacity of 1,000 cubic meters per hour each, and so to get to some 50% to this, so that we can decompose what's really decomposable. It means also to build additional 4 lines. It will be possible to do it somewhere. In some other places, for reasons of limited space, it will not be. So this is why it's necessary to have 2 ways to test the 2 methods, because of course, water-based technology will be more compact. So these are the 2 basic methods, either to increase the volumes, the load value, secondary treatment, or to build water-based line, coagulation line, also, and to remove the insoluble substances which cannot be oxidated and which cannot proceed to the stage of final filtration through the activated carbon. So now I would need that slide that I have been looking for. No, maybe what comes to my mind, in comparison of these 2 conditions, the Liberec and Amazon wastewater treatment plants, a little bit smile. You can see in the Amazon distribution center, and the people are really go for the drugs. So example, there's 2 or 3 times higher carbamazepine and tramadol concentration. Tramadol is not only painkiller, and it is also helps to release serotonin, and so psychopharmaceutical a little bit, and so these 2 substances are in extremely high concentrations there. So when we saw that, we said to ourselves, yes, they are abreast of times. Okay, I will go through what happens in Liberec. This is the operation of the pilot without the sorption endpoint. Of course, the forest of the peaks, that's the input, and what is at the bottom are detection limits for a number of pharmaceuticals. We are able to achieve 10, 20 nanograms. In some of the places it's worse. When we went to the pilot project, including the sorption endpoint, we used an ash bin, and so it worked, and so we got to some 4 months, only 4 months of a life cycle or the activated carbon. Maybe, hopefully it'll work now. I can't find what I'm looking for. So when we did it in laboratory, the maximum that we established was in controlled conditions. The life cycle of the active coal was only at the level of 5 months. So this is what I mentioned, Amazon and its high concentration carbamazepine, about 2 micrograms per liter, and Camandol 3.5 micrograms per liter, 2-3 times higher values than what we have in Liberec. And yes, and here we go. This is the long-term absorption test, the inflow in the absorption column, and what is at the bottom are the outflows. You must believe me. I hope that the presentations will be distributed so you can additionally search the details. And we were at the end of November, in some other places at the end of April, some substances we could see, clarithromycin specifically in this case. I'll deal with it, and I can confirm actually what was mentioned before, seasonal fluctuations very high. We had the highest concentration in the period of January to March, and was about 13.5. And what I'm mentioning here is the ozonization. And I want to show you on this why the final sorption is important in comparison with the results that I could see, the results from the Tomier Hospital when the carbon vanished very distinctly. So we could see the concentration up to 500 kilograms per liter. Ozone, 5 minutes, that KSK was dropping from 20 milligrams, that are quite routine outflow values in Liberec, to 12, for example, but not much happening about the fluctuations between 8 milligrams. What it means, all those substances are oxidized, the average carbon oxidation number growing, so actually the COD dropping, and the sum of organic substances, and not much happening about that, and everything goes on. And this is as far as the use of the oxidation is concerned. So about the proposal, some people say, fine, we will do AOP. Of course, it works. This UV test, if you actually overdo it, so in UV drops to 0. Logically, because the UV attacks the circuits and the double couples, and so it means now 20 kilograms per cubic meter, so it's untenable in terms of price, so we must be at 1/10 somewhere, so it can be at the level of the first kilowatts, and so it costs adequate sum of money. So this is the same we actually played with the dose of peroxide. It can be just low. That's it, 10, 50 milligrams per liter, and in this quantity it is effective, efficient. And this is summary. I will look what I forgot to tell you. Maybe I've told you everything. The most important is the middle one. for us to make it sustainable, to prolong to the max the life cycle of the activated coal and reduce the dose of activation agent in oxidation, we have to reduce the outflow of the organic compounds there, because as I mentioned, by dramatically increase the volume, increasing the volumes, or do the waterworks line coagulation with the follow-up filtration. And the most important one, the sorption line, is essential because because of the organic substances about which we know only little. We can't let them go further, and so the estimates in Switzerland, Germany, in the draft directive, the recommended methods are ozone and GAC, and it's about 20 crown increased cost per 1 cubic meter, which is unimaginable today. But short, water is cheap here. Water is cheap in Europe. Water is cheap in all the places, and our region has worked out with a socially tenable price. It's about 160 crowns. I don't know how they came to such a conclusion. It's the bottom, and 20-30 crowns higher than what we have today in Liberec. When I went there, it was 80-90 crowns per cubic meter. Now it's 130. So it's a matter of getting used to that, so that the water economists speak about that openly, frankly. The idea of the European Commission is that the payments will consist of from the taxes of manufacturers and distributors. We wonder how the mechanism will work. So this is how they proclaimed it, and so this is the end. Thank you very much for your attention. I wish to thank the Norway Grants and also the infrastructure of the South Bohemian University, with which we have cooperated to verify the validity of our analysis. So I want to thank them all, and this is all I wanted to tell you. Thank you very much. And also thank you for your patience in our presentation preparation. Now, ladies and gentlemen, the last round of questions which you can raise to Mr. Leder and Mr. Vashinka and Mr. Kvacek. Please, the gentlemen should come up here to the podium. Be so kind. So if you have no questions, you can actually raise it now.
Děkuji.
Tak dobrý den ještě.
Good afternoon. One more time, I would like to ask you about the operation costs. 20 crowns seems a bit too much to me. I know that in Switzerland, when they started with it, their costs were 0.2 of Swiss franc, which is much less, which is about 2.5 crowns. And in our research, we did some recalculations. We did it clearly on the ozonization technology, production of oxygen for ozone, and we had depreciations over 20 years. So the technology in total, without the reaction vessel, cost about 0.7 crowns per cubic meters. Without the GAU, it's not included. Of course, it will be also expensive. However, 20 crowns per cubic meters, it seems a lot to me. I also wanted to mention what my colleague Kvacek said. Did you actually calculate your operation costs in testing at the hospital? 2 questions. So who will start? I will start. When it comes to ozonization, I probably am not able to answer the question, so my colleagues will. When you take the phentosaline as a catalyzer, it is cheap. However, we need much higher concentration of peroxide. So it's dozens of crowns per cubic meter. So it is not effective. So it is better if you use other methods that may be cheaper. That's this part. This also includes increasing the volume. Does not mean only investment, but also more costs for aeration, because you need to air the whole mixture, which are great operation costs too. And I don't know about GAU. I don't know how they got to the numbers in Switzerland. One thing is where to find so much granulated active carbon. That's the first thing, and then at what cost. And regeneration in this amount is probably not possible. So I don't know. It's just an estimate on our part. And I may be skeptical, but I don't think it will be possible under 10 or 15 crowns. Mr. Kvaček, in Tomajer Hospital, do you have any ideas? I would like to tell you that I don't have specific figures available. The operation has been running for 2 months. We will definitely have information about consumption of electricity and utilities later. There are two things, though, I need to mention. It's not only about operation costs. They will probably be over 20 crowns per cubic meters, because we also have to include investment costs that will be enormous. So, and another thing is that is also essential in the proposal for the guidelines. A big part of these costs will be carried by the producers of the pollution, which are mainly pharmaceutical companies. And based on the dialogue between the European Union and these companies, they should be reflected in the price of the drugs. So that would probably help to make sure that it doesn't get too expensive. The majority of the costs now goes to ozonization, generation, and consumption of electric energy. In the case of GAU, it is unpredictable now. We cannot say in how long the technology will have to be changed. It is also another big expensive. In the Czech Republic, we don't have any reaction line yet, but I'm not sure whether we will be able to do this anytime soon. It will be necessary to take the operation costs in such a way that you may expect that it may become more expensive. However, it does have the effect. Any other questions? Czech Hydrometeorological Institute. You have all of you have mentioned the energy efficiency. These WWTCs should be energy neutral, as far as I know. Who will answer this question? Of course, the estimates are that some of the treatment plants will be independent. For example, in Pilsen, they have a lot of substrate available. They don't even take into account the increases in price. Our colleagues in Slovakia are against this because they should also do tertiary cleaning now for millions of crowns. If some big WWTCs use sludge, import external substrate, and help themselves to produce energy. I will add two things. In this case, the legislation is contraindicated. WW2 cities over 150,000 inhabitants, where the standards will be strictest for the quaternary cleaning will have to be assessed separately, and the technologies will probably change soon. However, in some cases nowadays, we try to get them to energetic neutrality. The quaternary grade is not there yet, so I'm a bit skeptic in this too. However, I think the sludge management may also move forward in the future. So we will see. It is a question of the next dozens of years. However, the technology will probably go forward in the future. Any other questions? Questions at the end of the conference? It is an honor to pose a question at the end, so I will pose it myself. It's a question for all three of you. What do you think such a conference will look in 10 years' time? I think that today was a lot about skepticism for the future. I think it is normal that we are skeptic because this is a new topic and it is negative. It is environmental pollution, and we try to address it, and we want money for it, so nobody can really perceive it positively. I believe in 10 years we will move here again. The technologies will be getting in operation. I think by 2033 we will already have big operation applications in some of the WWTCs in some regional towns that will be more advanced, and I believe that other things will appear, like membrane processes. I think that the investment prices may be even higher, but I'm sure that we will do the quaternary cleaning for sure. I think this will be about money. Now, when we have project calls, it's all about money. State budget also is cut down, so there's not so much money for research. This will be a big problem, and then who will pay for everything? When the price for water goes up, the question if people will be willing to pay for it. On one hand, there's environmental friendly approach, and then the operation costs, and then what people are willing to do. About the granulated active carbon, we had 325 kilograms. It cost 35,000 crowns without VAT. Together with Čevák, we have other tasks for the near future, and we will already have answers to some questions. What will it cost? So in Liberec, we will build a copy of the line. So we will have an opportunity to play with the technological processes in secondary and tertiary and quaternary cleaning. However, the question is what the investments will cost. What will happen if there is a water supply line available? I am optimistic. The problem is not to remove it. The problem is that after 3 months of cleaning at GAU, we don't know yet what to expect, and we will see the lifetime, what the lifetime is in case of GAU. We can do 2 milligrams at the outflow, but we will see whether it is necessary. So what will play a role is assessment of toxicity and what still remains in the cocktail. So I am optimistic. Thank you. Thank you for using the word the cocktail again. So thank you for your presence. Here's a present for you. I'm sure you will enjoy it. Thank you very much. Yep. A round of applause for the gentleman. Ladies and gentlemen, this is over. I would like to thank the Norway Grants, Czech Environmental Fund. I would just like to say that all the materials, presentations, photos, everything will be on the website. All participants will get a link, and we would like to invite you now to the Festival of EHP Funds in Norway on the 21st of September in Prague, in Výstaviště site, where you can expect meetings, workshops for children, and also a concert of Písko Mill Band. So I wish you all a nice Wednesday afternoon, and I hope to see you again in the future.